Good afternoon, madam.
Good afternoon, sir. I think
Sir, talk to Elias, sir.
Satyendran sir has joined.
Yeah. Good afternoon, Professor Satyendran.
I think he cannot. Sir, sir, Administrator sir, you can unmute Professor M. Satyendran. It's there. Oh, already he's in post-start. Okay, co-host.
Yeah.
Namaskaram. I can able to see. Good morning.
Yes, sir.
Good afternoon.
Since you didn't unmute,
What happened? Professor Kerela and Madam Bhagyalakshmi. How are you, Madam? How are you, sir?
Fine, sir. Fine, sir.
Fine, Professor Satyendran.
Just, I can unmute the camera just to make it fast, so I will change it. So I will come.
Don't tell students to follow up. And faculties other faculty. Fine. Get ready. I think we'll. Can you, madam? Can you tell groups are to call Elias sir?
Yes, sir. I will go on.
Elias sir number is there. Yeah, maybe another 5 minutes we'll wait and then we join up.
Actually, sir, our timing is like 3:30. Maybe he will be joining. He joined.
3:30. Yeah. 3:20. Oh, yeah, joining. Yes.
Sir, good afternoon, sir.
Sir. Good afternoon, sir.
Yes. Good afternoon, sir.
Hello, sir. How are you, sir?
Good afternoon. I just checking whether it is working. Okay.
Yeah, fine, sir. Yeah. How are you, sir?
All right.
Nice. Yeah. Our faculty, Dr. Bhagyalakshmi also is there.
Hello, Dr. Bhagyalakshmi. So it's at 3:30, right?
Yes, sir. 3:30. Yeah. Sir, we will start for plus or minus 5 minutes so that participants can join.
No problem.
Yeah. The another resource person, Professor Satyendran, also joined already.
Yeah. He wrote to me yesterday that he had be joining.
Yeah. He mentioned, sir. I also recommended your books to our library as well as I had my personal copy also.
Okay, very good.
I always tell that organometallic follow the Professor Elias. Organometallic, from the Delhi University Alberts, I used to tell them. Now recently I have seen a couple of other books also. I told them, our students also. We like to have you offline sometime.
Yeah, let the COVID go. Then I have not gone out for 1 year from my Delhi.
Yeah.
Okay, let me just. I have not used Zoom. Always we use. Okay. Let me just try to share the screen and see whether it is working. Okay.
Yes, sir.
Because we don't use Zoom, we always use other softwares. Okay, that's why.
Yeah. Here the advantage is we can accommodate as much as possible.
Okay, no problem.
So that's the. How is Professor Nagendran?
Oh, it's fine.
Yes, fine. It's visible, sir.
It's visible now?
Yes,
yeah, it's visible.
Kindly just move on to the next slide, sir. Let us see whether it is moving. Slides are moving. Yes, sir.
It's fine. Yeah.
Also, I just wanted to play a video and see if it is working. Okay.
Yeah.
Is it visible?
Video
not coming.
It's not coming.
Video not coming. 1 minute.
Okay.
Sunny, how to play the video? Can you, the coordinator? I will ask the Zoom coordinator. Sunny,
Sir, just he has to go to the video.
It is on.
Sir, basically, you have started your window share. That's why when we are not able to see your video. I request you to just stop your screen share and share your entire screen. You have shared a window.
yeah, if you share entire screen, then you can use.
Yeah.
Yes.
This is visible, right? It is visible.
You are now screen only Windows sharing is there.
Sir, no, sir. Sir, you stop the presentation and one more time re-enter, sir. While doing that, you just share entire screen. Now you can just stop sharing.
Stop sharing. Sir, first stop sharing. Yeah.
Okay.
Now share entire screen.
So just click on share. Then after sharing that, you'll be having a window where it is written desktop 1. You can just select that desktop 1, and from there you can share your entire screen.
Okay.
So all the activities which you are performing, if you just shuffle between the windows also, it will be visible to us.
Okay, let me try. I'm going to share the screen again.
Yes, sir.
Yeah. And then I have to see desktop 1.
Yep.
This PC, you're talking about this PC?
Yeah. This PC will work, sir. This PC will be there.
Yeah.
Okay.
Yeah. Yes,
Then
sir. Right now, your entire screen is visible to us. Now you can just shift to the PPT. You shift to the video which you are willing to share with us.
Okay, so video cannot be embedded inside the PowerPoint. That's what you're saying, right?
Yeah.
Sir, if it is already embedded, it can be played.
But I played, it was not visible.
Okay. Sir, actually, when we open the video, it just opens in a different video. That's why it is not getting visible over when you have shared a single window. So that's why if in this mode, it will be visible. I will.
Is the PowerPoint visible now?
No, sir. Right now, your window screen is only visible.
Okay.
Please get shifted to the window.
Madam, can you tell Kurup sir to join?
Yes, sir. I will inform him, sir.
Okay, 1 second. Is anything visible now?
Your screen only visible, sir.
Okay. Let me come out. I think then I will not show the video. That's better. Otherwise, there'll be problem. Okay. Okay, let me just share the PowerPoint. That may be better. I will not use the video. Okay.
afternoon, Professor Class joined. Professor Ilyas and Professor Satyendran, both of them there.
Okay.
Yes, sir, already joined long time back.
Hello, Professor Kurup. How are you?
Good morning, Professor. Good morning.
Hello, Mr. Ilyas.
Hello,
How are you?
Satyendran.
Good morning,
Fine,
Professor.
fine.
Good morning. Good morning. Good morning. Good morning. How are you,
So
Professor?
welcome.
Yeah, thank you. I'm just trying to figure out. I not use Zooms. I always use the Microsoft Meet. That's why.
Oh, please, Professor, please.
I am traveling some emergency work. That's why I am attending from my home. Sorry for inconvenience. I am coordinator. Please excuse me.
Is the PPT visible now?
Yes, sir. Your
No,
PPT is
sir.
visible.
It is visible.
Okay, I think I will not use the video then. I'll use the PPT only. Okay. Okay. Yeah, because I heard that if it is working on Zoom with Microsoft Teams, there's no problem because I given earlier. But Zoom has some problem with video. That is
Sir, can you just please retry playing that video?
on the screen on the PPT.
Yeah, on the PPT.
Okay.
And now it is loading, sir.
It is
now
coming
it's
now.
loaded. Yes, sir.
Is it
Now
visible?
coming.
Sand
Yes,
silicon.
yes. Sand to
Okay.
silicon. It's visible. Yes,
Okay.
sir. Yes, sir.
Yeah.
Now it's nice. It's coming, sir. It's coming,
Okay.
sir.
Okay. I'm back to the PPT, right?
Yes, sir.
Yes,
Now,
sir.
please.
Now back. Yeah.
Okay.
Yes, sir. Now
Yeah,
back.
I leave it there. See, in IIT, they are not allowing Zoom. Zoom is not allowed because there is some issue. So they said initially should not use. So we have all other software like Google, that is Google platform is there. Then Teams is one
So
use
Teams,
for even taking
yeah.
classes. Okay.
Yeah. Team also good actually. Many of them team in there using, sir.
Okay. So you tell me when to start, okay?
Sir, another few minutes now.
No problem.
3:30 settled. So
Yeah,
we'll
I
just
want to check
participants.
everything is okay.
Yeah. Yes, sir. Yes, sir. Sunny, can you unmute others? Only
Sir.
you. Yeah.
Yes, sir.
Can you unmute all because some people are playing with.
Sir, I have enforced that forced mute condition. I am removing that for now.
Okay.
You just tell me whenever it's all the people have joined in, we will enforcing that forced mute condition, sir.
Okay. You can unmute Professor Raman also. Dr. Raman is. Professor Ilyas said, Dr. Raman from he was also one of the resource person on the day one.
Okay.
From yes,
Hello.
Inorganic he talked. He is here.
Yes, sir. Thank you, sir.
So do you have a MSc program there now in Kasaragod?
Yeah, we have
Yes,
MSc
sir.
chemistry.
It
MSc
started from 2013 onwards.
Okay.
Now six group has already graduated, and PhD also 3 PhD scholars are already. One has already depended, and another 2 PhD scholars having depends in coming weeks. So 3 PhD scholars already completed. And we are in a now regular campus.
Hello.
Kurup, I once went to Cochin University and then you are not there. So they told me recently you had shifted to Kasargod.
Yeah. In 2017,
So
2017, I shifted.
So somebody else was head of the department. They said that year you shifted to Kasargod.
Yeah. You came for some Viva or?
No. I came for your annual symposium is there, no one-day symposium. I came for.
Okay.
I have a house in Cochin, so this is an opportunity to see the house.
Okay.
Okay. We are very happy to have you, sir. Thanks for immediate acceptance.
Sunday I'm free. Other days there will be something or other because currently I'm the head of the department also. So a lot of responsibilities. Okay, faculty hiring, everything is going on here.
How is Ramanan, sir?
Ramanan is retiring this year. This year, September, is retiring.
He is retiring this year. Sir? When I was in University of Delhi, I used to contact regularly. Now, little bit quite far away from that.
Sir, Saktivel sir,
yes,
we can start.
Yes, madam.
I think we can start. I think
another 3 minutes, madam. To 3:30.
Almost participants.
3:30. Yeah.
3:30. Now it's
3:30. Almost all participants.
Okay. Yeah.
So the participants are all students, or some of them students and some of them teachers.
Mostly teachers.
Actually, mostly teachers. Only, and our students we have permitted, and since Satyendran has requested, and we have because it's mainly for the teachers training.
I'm waiting for. I'm waiting, sir. Of course, I hope at least 20-30 students will attend because the regular class starts tomorrow onwards.
Okay.
So I sent a message yesterday. So please, it is nice opportunity for you people to listen, and you are going to follow your book only.
Oh, great! Thank you.
We have books, sir. We are completely following your book only.
Okay.
So last year, Professor KCT took the main book in the transition element, and this year again it came to me. So 1 year there was a gap.
Yeah, I am updating my web PPTs also. Every year when I teach, I keep adding new material to it.
Okay, sir.
I used to follow. I used to follow upon. Our another colleague, Dr. Ravikumar, also is there. Yeah.
Okay. I've been recently doing only main group chemistry, so that although my other book is more famous, Organometallic, I have not got opportunity to teach. My colleagues are all teaching it here. So maybe come out with a revised version of that book.
Organometallic is a wonderful book.
That is now old.
I have referred to your.
So you have to come out with the next edition. So only if I teach, chance to do it. So maybe in the, I am becoming 60 now. Another 5 years are there. So within that time, I have to do all the books now.
We are waiting, sir. We are waiting. That's
a great contribution for the society, sir. Yes, writing the book
doing it. It's more important. In life, whatever you do, you should be doing it. Okay, that's my philosophy. Okay, so that is I enjoy doing it. That's it.
So we'll go for technical session, sir.
Okay,
so right. Formally proceed.
Yeah.
Okay, sir. Thank you. Good afternoon, everybody. Professor Satyendran from University of Hyderabad. Thank you for accepting our invitation and joining in this webinar, even during the Sunday, because we know that you have a lot of commitments. Even during your commitment, you have accepted our invitation. Thank you very much, sir, for your kind acceptance and coming on even on Sunday and sharing the session. We are very happy to have, sir. On behalf of Department of Chemistry, on behalf of organizing committee, I welcome you, sir. Thank you, both of you, sir. And today, participant, we have two speakers. One eminent speaker, Professor Anil Ilyas, as already we are discussing. He has written so many books and on inorganic chemistry. And then Dr. M. Satyendran, he is my very close friend, as well as we were together in IIT. So we know last 2 decades each other. So both of them will be today delivering lectures. And today's session will be shared by Dr. M. Bakilshmi Madam, our colleagues and organizing secretaries. She will be sharing. So before going to the session, I just like to have a brief introduction about Professor Dr. Bakilshmi. So Dr. Bakilshmi associate with our University Central University of Kerala since 2013 onwards. She did her PhD from Anna University, and her area of specialization is electrochemistry, electrocatalyst, electrocatalytic reduction, electrocatalytic applications for the CO2 and electrocatalytic conversion of CO2 to fuel. These are some of her applications, her research, and she also focused on the physical chemistry teaching, physical chemistry as well as inorganic she is teaching. And for her credits, she has a 40 research publication, and she also handled several research projects. And she has completed 1 PhD students, and currently in her team there are 3 more PhD scholars are working. With this brief introduction, I request Dr. Bakilshmi to share the session. Thank you. Over to the Dr. Bakilshmi.
Thank you, sir. Thank you very much, sir. So good afternoon, one and all. It's going to be a very great evening for us today, because we have our eminent speaker, Professor Anil J. Ilyas from Indian Institute of Technology, Delhi. So to talk about him, already sir has given many some hints, all those things. So I'll try to detail it. We can talk like as a category, teaching, research, like that. With respect to teaching, that is what has to be highlighted here, because sir is recognized as a very good teacher, because he has been a recipient of INSA Teachers Award in 2012 by INSA. Okay, and then he is also a recipient of Best Teacher in Chemistry Award in 2013. It was sponsored by Tata Chemicals, Royal Society of Chemistry, so Association of Chemistry Teachers, like that. And then one more award also he received, like he received as a Teaching Excellence Award by IIT Delhi itself for the BTech students during 2013 and 14. So to contribute to his teaching, he has published many books already. Saktivel sir has briefed it. So the very interesting book is like Collection of Interesting General Chemistry Experiments. It was published by University Press in 2002. And also a basic organometallic chemistry concept synthesis and applications by Indian edition, University Press in 2010. And the recently the chemistry of p block elements, again it's by University Press Hyderabad in 2018. All these books are very fantastic, and even now I think our Satyendran sir has Professor Satyendran sir and our Professor Saktivel sir has started adopting that book for the course. So it is really interesting. So in a teaching means he is basically teaching that organometallic chemistry and its industrial application, organic, inorganic polymers, main group chemistry, p block elements, all those things. So he's a very good expert in that field. So this is with respect to his teaching. And when we talk about the publication, he has more than 80 publications. And very important is, if you see that he is equally contributing to in research also, both teaching and that his citation is around 1,000, and then his H-index is around 19. It's really a very good number to be recognized as a very good researcher. So it can be seen that he is very comfortable in managing both the research and the publications. So if you see his website, as sir told, he's really updating. So you can see that there are some problems in organometallic thing, so that each and every chapters he has given some questions, and also he has solved that. He has expressed everything in his website. So for a layman in inorganic chemistry, just to enter the website, he will get all the information, I hope. So this is with respect to his teaching, and very importantly, research in the sense, nowadays the getting projects is also very one of the tasks we should complete in our career. So Professor Anil J. Ilyas, he has completed around 10 projects funded by DST, Royal Society of Chemistry, CSIR, like that, various funding agency. He has contributed equally to the research projects also. So I feel that it is a really great thing that we have a professor here for us to hear something about the inorganic chemistry. Especially, I think he's going to talk about the same P block elements. Yes, he has displayed the thing also. So let us hear from him about the P block elements. I think everybody will be benefited by a good, excellent teacher today. Thank you very much, sir, for being with us. Over to you, sir. Please, you can take the session, sir.
Thank you, Dr. Bhagilashmi, for the kind words of introduction. It is indeed a pleasure for me to take part in this online training for college teachers conducted by the Department of Chemistry, School of Physical Sciences at Central University, Kasaragod. I have heard about this long time back because I also belong to Kerala. I belong to Kottayam, originally from Kottayam, but I have left Kottayam long time back. And also, Professor Kurup is a very old friend of mine who is right now in, and also Professor Shaktivel is very well known to me. So it's indeed a pleasure that I have been able to take part in this online teaching for college teachers. And what I intend to do today is to tell you something about how to teach the chemistry of P block elements. Okay. So let me straight away go to the slides. Yeah. So what is the objective of this presentation is that to highlight the importance of P block elements and compounds in our daily life and industrial chemistry processes. Number two, to demonstrate the relationship between properties and applications of P block elements and their compounds. How this chemistry has developed historically over the years and where it stands currently, a few glimpses of modern research in the area of main group elements, and for teachers, what is the best method to teach P block chemistry? Okay, and as Dr. Bhagilashmi mentioned, I have written many books, and my recent book is on the chemistry of P block elements, published a few years back. And most of the material which I am covering are given in this book. It covers all the P block elements in detail, especially synthesis, reactions, and applications. And if you have a copy of this book, it will be useful if you are a teacher and you want to impress students and also to see what is there to teach in P block elements. Okay. This book is available in Amazon and Flipkart and with all leading booksellers. And also there is another book on organometallic chemistry, which many research scholars and teachers are already familiar with. So I'm not going to talk about that. Today's talk is all about P block elements. Okay. So what does an average student think when he hears about P block chemistry? No, I have interacted with a lot of students, so I know the immediate response is very boring. Okay, lot of equations to mug up, starting from +2, when they take the NCERT book and see that the P block elements chapter and so many equations are there. So all these equations are to be mugged up. This my own daughter asked me this. Okay, I have to mug up all these equations. So this is all mugging. That's what they don't understand. They don't understand the importance of that. They're not enjoying it. Okay. And unlike coordination chemistry, there is no color, there is no magnetism, no high spin, low spin, no CFT. Oh, these are all beautiful aspects of coordination chemistry. You can have a lot of, color, origin of colors, splitting of d orbitals, magnetism, etc. Because nothing like that is there in P block elements. Okay. And if you look at the books, the standard book which everyone knows about is the Chemistry of the Elements by Greenwood and Earnshaw. Okay, Greenwood and Earnshaw both passed away, no new edition has come, but the size of the book, if you look at it, people get frightened. Okay, these are really huge books full of equations, equation after equation. So a teacher will always be confused as to what is to teach out of so many equations. Okay, Every reaction, every element, there are thousands of equations. And you look at any other book also, you see that wherever it is main group chemistry, it is equation after equation. So which equation is important? What is the relevance of this equation? How do you know what is interesting? All these are confusing to a teacher in PBlock chemistry. Okay. And somebody said something about boron, sulfuric acid, extra boring stuff, and what is the use of learning all this? This is a normal response you get from a teacher and a student when you think about PBlock chemistry. And I won't blame them also, because the way it is presented, often it is like that. People don't worry about what is the origin. So whenever you teach chemistry, what I found is that if you bring history into chemistry, how each equation which you see in a book is the painstaking work of some researcher sometime back in history. That time it was very important. Then it became an equation and got into a book. But now we only see the equation, so we don't know how it came. What is the importance of that? How is this chemistry developing? All this we don't know. So that's why when you try to tell the students also, we try to do the same boring way, mug up this equation, and students find it equally boring. So today I would like to show you how do you make PBlock chemistry interesting and how do you tackle each element. Okay. So how are PBlock elements different from transition metals? Okay. So transition metals are partially filled d orbitals. You have the unpaired electrons coming with that. And based on that, you get spectral and magnetic properties. And then when you think about applications, immediately homogeneous and heterogeneous catalysis, Wilkinson's catalyst, you talk about any catalyst, they're all transition elements for a long time. Nowadays, things are changing. Okay, that's what I'm saying. But generally, when you think about transition metal, it is all about homogeneous, heterogeneous catalysis. Whereas P-block elements, you see that we have partially filled p orbitals and filled d and f orbitals. There are no spectral and magnetic properties, and there is generally it was not there homogeneous and heterogeneous catalysis, but now things are changing. Okay. Now, so how do you compare the industrial applications? So one of the basic differences between transition metals and p-block elements is the industrial applications. Okay. So if you look at transition metals, all transition metals except iron are considered to be toxic to human beings. Okay, so iron is there, we know iron is required, people take iron tablets. And industrial application, if you look at it, bulk usage is in iron and steel. Okay, because construction, if you want something which is sturdy and permanent, which is really strong, you require steel. And that is in construction itself, you see a lot of iron and steel being used. Then there are alloys which are used, and then there are additives like titanium dioxide is an additive which is to make white paints. And of course, as I mentioned, homogeneous and heterogeneous catalysts, magnets and materials. Okay, but if you compare this to p-block elements, chemistry p-block elements and their compounds have a very large number of real-life applications where the elements and their compounds are used in bulk quantities. That's the difference. Using in bulk quantities, I'm going to define how much is this bulk quantities we're talking about. Whereas as far as metals are concerned, the only thing which you use in bulk is probably iron and steel and maybe a little bit of copper. But compared to that, the amount which you use in p-block elements is really huge. So bulk usage, when you think about it, is p-block elements which actually really stand out. For example, fertilizers, building materials, transportation, aluminum, for example, semiconductors, solar cells, explosives, pesticides, LED lights, touchscreen devices, inorganic polymers, fire retardants, disinfectants, nuclear fuel manipulation, storage batteries, refrigeration, all these applications you are encountering p-block elements and their compounds. That's why the modern day, you cannot live without the p-block elements, especially when you think about day-to-day, your life. Okay, so here are some of the specific examples. Boron, for example, is used as a control rod in nuclear reactors, because if you need to control the nuclear reaction, that means you need to take out all the thermal neutrons. So whenever you hit a uranium with a neutron, three new neutrons are produced. So a boron 10 isotope is able to absorb 2 of them. Aluminum is the modern day material for making movable components. Like earlier, our trains and cars were made of steel. Now we found that steel is too heavy, and if you want to transfer anything which is moving, if steel is there, you need to give a lot of energy. That means lot of fuel need to be burned. So modern trains, if you try metro trains or if you take modern cars, etc., they are made of aluminum, and aluminum also is getting replaced now with another material. Okay, carbon fiber reinforced plastic. I'll briefly talk about that also today. Gallium is now a very sought after compound because our LED lights, okay, are having gallium nitride in it. And nowadays, any human being worth his salt will be having a smartphone in the hand. Okay, so in the smartphone, the technology of smartphone, where you have the touch screen technology, it works because of one material called the indium tin oxide, ITO, Indian tin oxide. So it's so much of smartphones are being used now that people are worried that the available indium on the world is not soon going to be finished. Okay, that is the exponential use of smartphones. Okay, even the uneducated people you see anywhere, they'll be using smartphones, because to use a smartphone you don't even need to type anything, you need to only touch. Okay, so that's why it has become so popular, and the usage is increasing, and here again use of indium comes into being. Nitrogen fertilizers, okay, phosphorus fertilizers, silicon-based solar cells, silicon-based I mean parts of electronic circuits. Germanium is nowadays very important because it is used in fiber optics. So fiber optics is what is making me to reach Kasargod or anywhere else within a flash of a second, because the data is transferred nowadays through fiber optics. Okay. Lead was used earlier as an additive in petrol, which was banned, and now lead is the main component in lead acid batteries. These batteries are what is there in every automobile. Okay, and inverters which you have in your house and offices. And fluorine has many applications today. I'll be touching upon a few of them. And most maximum usage of fluorine nowadays is for freons or refrigerants, which keeps your rooms cool or your refrigerators cool. Chlorine, nowadays with COVID, you have a lot of requirement of chlorine-based disinfectants. So disinfectant area, chlorine has really become important. Oxygen is very important, and one of the very common use of oxygen is an antifreeze or a coolant. This is some of the examples that I'm telling you, and where you actually see real life applications of main group elements. So when you tell a student that these are important, then I think they'll be able to appreciate why we are learning main group chemistry or the P block chemistry. Okay, this is a periodic table I made of the P block elements. So you can see that again, except the three red elements which are toxic, all the others are something or other as application. I already mentioned boron, aluminum was there in aeroplanes, trains, gallium, LED, solar cells, indium is Indian tin oxide I mentioned, carbon molecular seeds, there is another material which is now coming up, carbon fiber reinforced plastic. Nowadays, the modern aeroplane is made of carbon fiber reinforced plastic, when aluminum is getting replaced by this carbon material. And silicon, as I mentioned, solar cells, silicon polymers. So it is becoming a component of many applications, silicon polymers. Germanium, infrared light and fiber optics. Okay, lead I already mentioned. Nitrogen fertilizer and explosives. Explosives again, without nitrogen you cannot make any explosives. And phosphorus fertilizers, fire retardants, and bismuth is a lead substitute now because lead is toxic. Oxygen I mentioned. I will mention more about that. Sulfuric acid. So like that, and fluorine is nuclear fuel, pharmaceuticals, polymers, refrigerants, and chlorine, PVC, polyurethanes, disinfectants, okay, and bromine and fire retardants. So you can see that every element, almost all the elements which is there, of course, even arsenic has an application of gallium arsenide, okay, which is actually a solar cell material. Okay, so you can see that there are a lot of applications, and these applications are not just a small amount of the material needed for a reaction like a catalyst, but in large quantities. So let us look at what do you mean by these quantities. Before that, what you see here is that as every one of you who is attending this talk is unique, okay, everyone is different from the others. Like that, you see, in organic chemistry, when you learn, you need to worry about carbon and a few other elements. Okay, if you know the properties of carbon, you can explain organic chemistry to a large extent. But in main group chemistry, every element is different from the other element, and every element has its unique properties. And the unique properties again related to some application. And you can see that that is seen in what I'm showing here. For example, electron deficiency is related to Lewis acidity. Okay, you have boron, aluminum, etc. Good strength weight ratio, aeroplane making. So the first flying aeroplanes were made of aluminum or an alloy of aluminum, because which had us the same strength as steel, but much, much lower weight. That's why human beings were able to fly. Okay. And another very important property is band gap. Band gap, when you have suitable band gap in semiconductors, you can have either solar cells or LED lights, etc. All depends upon the band gap. And then transparency and conducting property. That's what is there in indium tin oxide, which is there in your smart screen of your mobile phone. Or if you have even ATM machines, you know, the touch screen technology is all done by indium tin oxide. Of course, there's a lot of talk about graphene replacing it, but till now it has not done. Okay, it is still only in the experimental stage. What is right now there in your mobile phones is indium tin oxide. And fertilizer, essential element for plant growth is fertilizers. Okay, and you have nitrogen, phosphorus. Relatively low bond enthalpy is a property which is made use of in making explosives. And high electronegativity, that is something which is unique about fluorine, which makes less weak interactions. So that's make a volatile compounds like freons, which are highly stable also. And because high electronegativity means much stronger bonds also. And high nuclear cross-section, that is a property of certain elements like boron-10, which has the capability to absorb neutrons. Okay, and that way it can reduce the intensity or the exponential intensity of a nuclear reaction. And then there are compounds, there are light elements which are light sensitive and generating free radicals. It can be good or bad, but often it leads to very, very interesting chemistry. For example, chlorine chemistry. Whenever you know chlorine chemistry or bromine chemistry, you think about the free radical formation when light hits on it. Okay. Now, if you, this is some comparison which I made and which I put up in my book. So if you take the top 15 chemicals made by human beings now, okay, in bulk, you will see such a list which I have shown here. Cement, for example, is used in 36,000 million metric tons. I'm using a terminology here, million metric tons. What is a million metric ton? 1 million metric ton, okay, is about 1 followed by 60 tons or 1 lakh tons. And if you, in Kerala, you know, elephants are there. If you compare, to get a realistic picture, 1 elephant is 5 tons. So 1 million metric tons is about a weight of 2 lakh elephants. Okay, you can assume 2 lakh elephants. Okay, maximum you might have seen is only in Trichurpuram, but you know, if you have 2 lakh elephants are there, that much you can see will be a 1 million metric tons. So in that scale, if you look at it, the only transfer metal which is used in large quantities is iron in steel. But sulfuric acid, for example, is one of the number 2 chemical, okay, which is produced almost 2,200 million metric tons. Okay, so you can see in terms of elephants how much it is. Next one is ammonia. This is the current, I mean, this is in 2010 and 2013. It's increased now, maybe 150 million metric tons it has come. Sulfur, nitric acid, okay, glass, chlorine, phosphoric acid, aluminum, hydrochloric acid. Okay, these are the chemicals which are made by human beings in large quantities and being used in our industries and day-to-day applications. So now let us look at things. Where is all the sulfuric acid going? 200 million metric tons of sulfuric acid. If you look at it, is 60% of that goes for making phosphate fertilizers. So you can see that NPK, if you remember the 3 elements, nitrogen, phosphorus, potassium, so much of phosphorus is required. Sulfuric acid is the reagent which is used to convert the phosphorus-based ore to a useful soluble phosphate, maybe phosphoric acid or a phosphate. And ammonia, the Haber-Bosch process, which is actually the way of converting the atmospheric nitrogen to ammonia. And 80% of that ammonia is going for fertilizers. And then another a quantity goes for making nitric acid. So nitric acid again is required for nitration, and nitration by nitration is how you make explosives. Okay, almost all the explosives except for a few hydrogen peroxides, you will see that nitrate salts are, or the nitrate compounds are the explosives. Sulfur again is used for making sulfuric acid, and the sulfuric acid is again used for making phosphoric acid. Okay. Nitric acid again is used for ammonium nitrate, which is used as fertilizer and also as an explosive. Glass, construction. Chlorine, again, chlorine. The major use of chlorine is for making polyvinyl chloride, PVC. It is a number 3 polymer in the world as far as mass production is there. Number 1 is polythene. Number 2 is polypropylene. So there are also many other compounds which can be made from chlorine. And if you look at the ammonia, 50 million metric ammonia is produced. Ammonia is hydrogen is used for making ammonia. So now we can see why these two are become very important, sulfuric acid and ammonia. Phosphoric acid again obtained from phosphate minerals, okay, hydroxyapatite and fluorapatite by reaction sulfuric acid. And that is again used for making fertilizers. Aluminium, construction. Hydrochloric acid again for PVC manufacture, etc. So if you look at the current production of chemicals in the developing world or the developed world, this is the number you get. And you can see these numbers are given in million metric tons or MMT. And that's why there is a huge quantity of chemicals are being produced. Okay. And this, many people are not aware why this, because now when we talk about fertilizers, okay, we say we use only biofertilizers, we only use cow dung. Okay, this is useful if you are doing your back house in your vegetable garden at your home. But when developed countries cultivate their land, they cultivate in huge spaces. Okay, you cannot imagine that, and it's all mechanized farming. There you need fertilizers, and these are the fertilizers which are there, which will come to your use. And that is why they are being produced in the world in such large quantities. Okay, now let us look at some of these applications. Application of P-block elements in bulk are highest in the development of synthetic fertilizers. Okay, sulfuric acid, so the NPK stands for that. Sulfuric acid, ammonia, hydrogen, phosphoric acid, all lead to fertilizers. So you can see that the fertilizer industry, if a country has to develop, then you need to have food produced. That's why now there's a lot of talk about farmers. Okay, the country is dependent on farmers. If farmers don't produce wheat, you and me don't have anything to eat. Okay, that's why cultivation is extremely important and fertilizer equally important. Okay, now when you look at these fertilizers, the father, this historical is very interesting. The father of the chemical fertilizers is Justus von Liebig. Okay, so Liebig in 1840 came out with a book called Die organische Chemie in ihrer Anwendung auf Agrikultur und Physiologie. That means organic chemistry in its application to agriculture and physiology. In this book, he for the first time identified 3 elements, nitrogen, phosphorus, potassium, as essential for plant growth. And that is how all these fertilizer industries, to make fertilizers started. Before that, people are not aware that what is the need of a plant. Okay. And Liebig has again some other very interesting findings. For example, there's something called Liebig's barrel. Okay. So he, see, how did you get this ratio that nitrogen, phosphorus, and potassium should be at best in most of the cases like 3:1:2. See, this is again, he came out that with the suggestion that the growth of a plant is related to the availability of the element which is among these, which is the minimum. That's why it's called Liebig's barrel. We say that the level is always here. because if one particular element among these three is small in quantity, or lower in quantity, then the plant is not going to have full growth. That is how he realized it and informed the people who are doing agriculture. So, and again, they say that he has another very interesting job, because he is the person who started the first practical chemistry laboratories. Okay. So the Liebig taught the world two great lessons. Number one, in order to teach chemistry, it was necessary that students should be taken to a laboratory. So that's why we take our students to laboratory, because you cannot just read book and learn chemistry. You need to go to the laboratory and do it. This is a picture of the first chemistry laboratory. You can see how, how people are sitting there, no lab coat, no nothing, okay, sitting, standing, leaning on the bench, which you don't allow nowadays. Second thing which Liebig mentioned is that to apply scientific thought and method to industrial problems, one must have a thorough knowledge of the sciences. That means only if you know the sciences, you can apply it to industrial problems and find out solutions for that. Okay, so that's what that was what what Liebig taught us. It was said by another great scientist called Ira Remsen. Okay, now the first synthetic fertilizer was made by Sir John Bennett Laws. So this is a very important equation. Okay, here taking what is known as the calcium phosphate or hydroxyapatite. If this X is OH, you have a hydroxyapatite. If X is fluorine, you have a fluorapatite. React with sulfuric acid and water, you get phosphoric acid, and HX can be water or hydrofluoric acid. So hydroxyapatite looks like this, and fluorapatite again looks like this. Today, I'll also talk something about fluorine, okay, or fluoride. And you can see that your teeth is made of hydroxyapatite, and when you apply a toothpaste containing fluoride in it, the outer covering of the teeth is getting converted to fluorapatite. And that is the chemistry, why it is, and all I'll talk in the later part of this talk. So this equation is called a $1 billion equation, because as you saw, the amount of sulfuric acid the world produces, and all the 80% or 60 to 80% of that is used for doing this reaction to make phosphoric acid. And from the phosphoric acid, you make phosphate, okay, triple phosphate, single phosphate. You have heard these names normally mentioned by farmers. So sulfuric acid, therefore, was one of the very early chemicals to be prepared. And there are many ways of making sulfuric acid. One can say that sulfuric acid is the mother of all acids. For example, it can be obtained by oxidation of iron pyrites, which is also known as the fool's gold, or it can be obtained by heating green vitriol, that is FeSO4 And industrial way of making sulfuric acid initially was by burning sulfur in the presence of potassium nitrate and steam. So basically, you can see that potassium nitrate again was one of the early chemicals which are used. So potassium nitrate, how people obtained was it from guano. So what is guano? It is another name for potassium nitrate or saltpeter. Guano is nothing but accumulated bird excreta. Okay, there are islands and islands in the oceans where seabirds have been there for ages, and they have been excreting bird excreta. It accumulated over the years, and one of the ingredients of that is potassium nitrate, which can easily be crystallized out if you use bird excreta. So you can see that in the olden days there was not many chemicals for people to work with. Okay, so whatever they have, including bird excreta, they used to get chemicals out of that and do the chemistry. And of course, if you look at all these methods, what happens here is that sulfur is getting oxidized, sulfur dioxide oxidized further to sulfur trioxide by an oxidizing agent. Sulfur trioxide dissolves in water, forming sulfuric acid. That's how it is being made. Now, sulfuric acid is again react with sodium chloride gives hydrochloric acid. Sulfuric acid with potassium nitrate gives nitric acid. Sulfuric acid with hydroxyapatite gives phosphoric acid. So you can see that that's why it is said that sulfuric acid is the mother of all acids. If you have sulfuric acid, you can make any other mineral acid. Okay. Now, ammonia. Ammonia can also be said as the mother of all nitrogen-based compound, because nowadays all industries are dependent upon ammonia. Okay, and the synthesis of the Haber-Bosch process, first discovered by Fritz Haber, and later on made into in the industrial scale by Carl Bosch, is taking atmospheric nitrogen and reacting with hydrogen in the presence of a iron-based catalyst. Okay, that is a magnetite catalyst, and gives you ammonia. And this has become so much important in our day-to-day life. Both Haber and Bosch received the Nobel Prize. And according to an estimate, what they say is that 60% of nitrogen present in human tissue has its origin from the Haber process. So you can say that from where the nitrogen came, okay, it can be 60% right now is from the Haber process. Because you would have used ammonium-based fertilizers like urea to grow food. That is a food which you eat. That way, the ammonia, the original ammonia, gets into your body. And it is more than 140 million metric tons are being produced in the world. And another very, very interesting estimate is that if there was no Haber process, the current population of the world is somewhere around 7 billion. Out of that, 3 billion people would not have survived. They would have died because of hunger. Okay, if we hear about famine long time back, maybe before you were all born, before I was born, 1930s, 40s, you had even the famine in Bengal. There was famine in India, famine in many places in the world. So food was not there. So this production of fertilizers made sure that you can grow food or you can cultivate properly and get good yields, and then you can feed the population. That's why if there was no Haber process, so they say that it is one of the greatest discoveries of human beings is the Haber-Bosch process, because if it was not there, 3 billion people would not have even survived. Okay, so in today's talk, now with this introduction, I will go to selected, a few selected topics. I will go quickly because I think some time was wasted in the introduction. So I will be just briefly touching upon these 5 elements and trying to impress upon you what is interesting about these and how do you make students get interested in these elements. So what is so important? Why do you learn these elements? So starting with silicon and ending with chlorine. So if you look at the properties of silicon, silicon is a semiconductor with a band gap of 1.1 electron volts and find use in solar cells, fabrication, electronics. And silicon forms non-toxic organoderivatives. That's very important because non-toxicity of organoderivatives that find use in a wide range of applications. That is why silicon polymers, the inorganic polymers which are widely used, are non-toxic. Okay, silicon oxygen bond is one of the strongest bonds based on silicon. So these silicon polymers having a SiO backbone are the most widely used in organic polymers. And what is so special about these inorganic polymers over organic polymers, which you learn when you learn inorganic polymers, is that they have wide temperature range, or the glass transition temperature, which you normally talk about, the temperature at which a polymer becomes rigid when you cool down, is very low. The lowest for a silicon polymer, and they are non-toxic and they are water repellent. So they have a lot of applications. And then there are silicates. Okay, so siloxanes will have at least some organo groups like methyl groups present on the silicon, but silicates are totally inorganic compounds. Aluminum silicates, when you have a few silicon replaced by aluminum and a counter ion comes there, they're highly environmentally friendly and many of them are naturally occurring because the earth itself, if we look at it, is nothing but aluminosilicates. Then you heard about zeolites. You learned zeolites are open framework aluminosilicates, have pores and cavities of specific dimensions which can act as molecular sieves and bring about shape selective catalysis. So I'm just showing here how we actually make a solar cell, because if you look at our institute or most of the institutes now, is the roof of almost all the institutes, especially in our institute, is full of solar panels. And in Kerala, it has another great advantage. I don't know about Kannur Airport, but definitely Cochin International Airport is completely supplied. The electricity is completely supplied by solar panels. Okay, how do you make it? You stand with silica, silicon dioxide, sand. You make crystalline silicon, or what is known as ferrosilicon. From that, you purify it by distillation, go to monocrystalline silicon. This cut into silicon wafers, then fabricate into solar cells. So in the production of electricity from solar panels, India is right now number 5. So see, India's solar energy production in 2020 is 35,000 megawatts. Okay, and our target is by next year should be 100. or 1,000 megawatts. And if you compare that, the hydroelectric power is only 50,000 megawatt, for which Kerala is very famous. Even the Moolamattam power plant in Kerala is producing only 780 megawatts. And the Koina project is one of the biggest projects in India, which is only 1960 megawatt. Okay. Now, so the basic chemistry is very important, which you shouldn't. So when you take silicon dioxide or sand and reduce with carbon at 2000 degrees centigrade, you get the metal called ferrosilicon, which is having iron as impurity. So how to remove the iron? That is done by chlorination. So if you chlorinate it, you get silicon tetrachloride, which is a liquid with a boiling point of 58 degrees centigrade, and iron chloride, which is a ferric chloride, which is solid. So one is a solid, other is a liquid. We can easily separate this liquid and purify it by distillation. And again, if you react the silicon with the hydrochloric acid or HCl, you get trichlorosilane. This is again another liquid with a low boiling point. So the point is that once you get a liquid compound, its purification is very easy. Long time back in India, we used to do this, but later on it was found that it is more economical to buy from abroad. That's why these industries are not very prominent in India. When I was a research scholar and then after completing my PhD, I worked for a short time in Matur Chemicals, and they had actually that time started this process of making silicon solar cells in India by using the same method. So once you have this HSiCl3 at 1150 degrees centigrade, it gives silicon, HCl and SiCl4, and this silicon is what is being deposited. Okay, I just tried to show you a video where you can see how this it is made by Intel, how microchips are made from silicon. I hope it works. Okay. I think that's a problem. Okay, leave it. I think there is an issue with the video, so I will not show it. So silicon, the other very important property of use of silicon is in silicon polymers. Okay, so this the story says that Stanley Kipping, who was one of the very early chemists who was working trying to make the ketone analog of silicon. That is, ketone is R2CO, and he wanted to make a silicon. Even gave the name also silicon, ketone, and silicon rhymes well now. But although he did whole life he dedicated to make this compound, he was never able to make it. Instead, he was getting a very waxy solid, waxy semi-solid. So he got a colorless glue-like product was obtained, and there was silicon oxygen silicon bond. So Kipping gave the word for the silicon polymers, and after 30 years of his research, on the occasion of his retirement, he gave the Bakerian lecture in the Royal Society, where he said that we have considered all the known type of organic derivatives silicon, and we see how few are their number in comparison with the purely organic compounds. Since the few which are known are very limited in their reactions, the prospect of any immediate and important advance in this section of chemistry does not seem very hopeful. So what that is basically saying that I did 30 years of research, I did nothing, I got nothing. Okay, but he did not know what happened afterwards. In 1943, after a few years after his research, the Dow Corning company took up the industrial production of silicon polymers. And now, world silicon polymer demand is around $15 billion US. It is that much is the demand for silicon now. Okay, $15 billion US. So it's a wide range of applications are there. And this compound which he was trying to make, which is having a silicon oxygen double bond, became one of the greatest challenges for synthetic silicon chemists. And they gave it a different name, silanone. Okay. And the first synthesis of silanone happened in 2014. Nowadays, you can see more and more examples of silanones coming out. So this is a very tough synthetic challenge or research challenge to make this SiO double bond, because Si always form a single bond like this, SiO-Si bond. But it has a lot of industrial applications, and this is how you make it. You take dimethyl dichlorosilane, hydrolyze it, get this 8-membered ring. Then you do a polymerization in the presence of hexamethyl disiloxane. You get the PDMS or polydimethyl siloxane, which is what is known as silicon polymer. There's the lowest glass transition temperature for any polymer, which means that it will not lose its flexibility even at minus 123 degrees centigrade. That's why if you have to do something at a very low temperature, you better use a silicon polymer, not the normal polymer. Normal carbon-based polymers all will become brittle because their glass transition temperature is higher than minus 123 degrees centigrade. Okay, so why this was possible again is of a landmark discovery. This was done by Rojo and Muller, Eugene Rojo and Muller, called the direct synthesis. It's very important. It's a fundamental chemistry of silicon. We cannot miss this reaction. All this was possible because you should know that whenever a laboratory reaction is made into an industry, the industry always looks at how cheaply you can make it. If it's a very costly method, no industry will like to take, because industries always want to make profit out of what they do. So to make the starting metal for make the silicon polymer, this method by the Rojo and Muller called the direct process became a classic method. See, methanol and hydrochloric acid, if you react, you can get methyl chloride, and this is again available from natural sources. In the presence of a silicon copper catalyst at 300 degrees centigrade, it gives methyl chlorosilane, and these are some of the methyl chlorosilane. Out of that, the major product is dimethyl dichlorosilane. So this dimethyl dichlorosilane is the propagating group in a silicon polymer. So by this method, by the Rojo-Muller process, one could make chloro or silicon polymers very, very inexpensive manner. That is how the industry developed. As I mentioned, it has now become $15 billion US. Okay, now there are different types of silicon polymers. For example, silicon fluids are there, silicon oil, we say, silicon rubbers are there, which tubes are made, and again, silicon is again used when you want to cast something, because you want to make a shape or something, you always use silicon rubbers. Especially masks are now made with silicon face mask, not the one which you're using for corona. You're getting a totally, you can have the face of a film star if you use a proper mask. Then silicon resins. You see this burger advertisement in the TV. Burger says that their paints have silicon. It is not silicon, it is silicon. There an E is missing there. Please remember, they just advertisement fellows don't know any chemistry. They simply say silicon. It's not silicon, it is silicon, which makes you say that the typical advertisement which comes in Malayalam channels. Okay, my house is having a burger paint so that there is no fungus on that, whereas your house is not having that, so there is fungus on that. All that is silicon polymer. So remember that. And there are many other applications. But what they say that the first human print on the moon was made with the silicon salt shoe, because see, the moon temperature, like the Mars temperature now we talk about, varies from minus 153 to plus 121. So when it goes very cold, if the person who is landing on the moon is wearing a normal rubber shoe, the shoe will become very rigid. You need a flexibility for the shoe. That the shoe soles were made of silicon polymers. And nowadays, the LED bulbs also has a lot of silicon. This is silicon oil, what you see. Okay, and razor blades are remaining without rusting because of the coating of silicon polymers. Lipsticks. This is the breast implant. Okay, which is made of silicon. This contact lens, flexible contact lens, which can be used for a month, made of silicon polymers. And almost all face masks you see in movies are made of silicon polymers, because silicon polymers have the property that oxygen can get through it, whereas water molecules cannot get through it. So if you are wearing a face mask, with you can wear it continuously, you won't sweat, otherwise you will sweat. So there are a lot of applications, and wherever as a sealant it is being used, and wherever water repellency is required, silicon polymers are used. So it's one of the most wonderful compounds which have been the product of main group chemistry. Okay, now something about what is research going on nowadays, because if anybody is interested in research, people are trying to make now low valent silicon chemistry. Okay. So for example, this is what is called silylene. Silylene is divalent silicon chemistry. Okay, these are not known because silicon is normally tetravalent, tetracoordinate. Whereas here is a divalent silicon with a lone pair on the silicon called silylene. And this is a relatively new, very new entry called silylone. Silylone is a silicon in the zero oxidation state, which is stabilized by the groups known as N-heterocyclic carbenes. This is somebody might have taught you. One of the very well-known ligands in organometallic chemistry these days called the carbenes or NHCs, N-heterocyclic carbenes. So the N-heterocyclic carbene is able to stabilize the silicon in the zero oxidation state. And this is what I mentioned about a silanone. Because silicon oxygen double bond was extremely difficult to make. Only 2014, first they made a real silicon oxygen double bond, and that is called silanone. Oh, there are many such chemistry coming in my own department. Professor Nagendran, my colleague here, is recently made a first anti-cancer drug, which is made of a germanium. So silicon germanium has a lot of similarities. This is a water and air stable anti-cancer drug. So normally people think that working with low valent silicon chemistry is difficult because they'll be very, very sensitive or very, very sensitive to air and moisture, because normally people work in what is known as a dry box. Dry box is a big box in which nitrogen is filled, and then the gloves are there. With the gloves, you enter there and start doing manipulation of chemicals, etc. But now what I'm trying to say is that those times are now going to chemistry which is water and air stable. And that is how this new compound has come very recently from our own department. Okay, now let me now give you a glimpse about the nitrogen chemistry. So much about silicon. So I'm not going to cover everything because, as I mentioned, all these elements, each element I can give a lecture for about eight hour lecture. That much material is there, interesting material, application material, new developments. But whole idea of this lecture is to impress upon you, how do you make this chemistry interesting? So that's what I'm focusing more on, the applications. And if you know the application, then you can get more information by searching on that and get further interest on the topic. So nitrogen is available in the atmosphere. 78.09% of the atmosphere is made of is nitrogen. So unlike oxygen, nitrogen is quite stable in the atmosphere and does not get involved in chemical reactions. So it over the geological times, it actually build up in the atmosphere, and it uses a blanketing gas for maintaining an inert atmosphere in metallurgy. But when you think about the applications of nitrogen, there are three important applications. The number one is fertilizers. Fertilizers, ammonia, urea, and related compounds. Starting with ammonia, the whole chemistry goes. Then explosives. Okay, every explosive, unless otherwise it's a peroxide-based explosive, which are very, very few. Almost all the others are organic nitro and polynitrogen compounds. And then the third application, inhalation anesthetics, that is nitrous oxide, N2O. N2O, the other name is laughing gas. So this laughing gas also is used in dentistry and in operations as an inhalation anesthetic to make you not feel the pain when an operation is going on, or to make you unconscious. Yeah, and once you think about the nitrogen chemistry, the most important thing to remember is that N triple bond N is the second strongest bond known, and it has a bond dissociation enthalpy of 945 kilojoules per mole. You never find the only other stronger bond than N triple bond N is C triple bond O, or carbon monoxide. But you will see that as far as inertness is concerned, nothing matches that of N triple bond N. And nitrogen is an essential element for life and present in amino acids and proteins. And ammonia is one of the most industrially important inorganic compounds and a precursor to all nitrogen-based compounds. Okay, so that's why if you have an ammonia plant, that is sufficient to make any nitrogen-based compounds in the world. So that's why this Haber-Bosch process has become very, very important. Of course, you know about nitrogen fixation, and when you look at an explosion, when you look at any explosion for that matter, you will say that the formation of the N triple bond N is the driving force behind the detonating property of all nitrogen-based explosives, because at the end product is N triple bond N, and the bond energy difference between an N single bond N and an N triple bond N is what is coming out in the form of energy when you have an explosion. Okay. Now, so this is a very important process when you think about ammonia, what is known as a Haber-Bosch process. So Haber, whose life is itself something which has come out in movies because it has wide controversies and interesting material. So BBC came out with a program about his life called Bread from the Air and Gold from the Sea, the Chemist of Life and Death. Okay, he was called the Chemist of Life and Death. So sometimes I show these movies of Fritz Haber's life in the class. Students really get amazed. What sort of a man was Fritz Haber? Okay, as I mentioned earlier, if there was no Haber-Bosch process, 3 billion people of the world would not have survived. They would have died of hunger. The same man is also well known for another notorious thing. I'll come to that a little later. So this nitrogen from the air and hydrogen from natural gas, they are mixed and then they are passed through a iron catalyst at 400 to 450 degrees centigrade and 200 atmosphere. And once the ammonia is formed, the gases are cooled, and while cooling, the reaction is driven to the forward direction. That is for the Le-Chatelier's principle. Okay, you know that the fundamental equation. Okay, so when see about chemical equilibrium and all that, so Le-Chatelier's principle. So if you when a constraint is applied to a system in equilibrium, the system will readjust itself to nullify the effect of the constraint. I think you remember this theory of Le-Chatelier. So the constraint is that you remove the formed liquid ammonia, and that way you drive the reaction in the forward direction. So this is a method by which you make ammonia N2 plus 3H2 giving 2NH3 and high pressure, high temperature, magnetite as a catalyst, and each pass 15% conversion, overall 97% conversion. So this is the very first reactor in which ammonia was made, which is there in BASF in Ludwigshafen in Germany. No, but as you know that this is available everywhere. In fact, FACT in Alway in Kerala, they also follow the same Haber-Bosch process. Ammonia is again one of their products. Ammonia or urea is one of their products. So you can see that ammonia is the basic material with which you can make many things, many nitrogen-based compounds. These some of the inorganic compounds. For example, urea. How do you make urea? Urea is reaction of ammonia with carbon dioxide, giving ammonium carbamate, and then removing water from that gives a urea. So urea can be said as a solid form of ammonia because when it decomposes, it releases ammonia. And that is why, and see, the difference between ammonia and urea is that ammonia is a low boiling liquid, okay, or rather low boiling gas. It at room temperature gas, it has only at minus temperature is liquid. So if you need to handle ammonia, you need a cylinder. Whereas urea is a crystalline solid. You can easily handle it, carry it in a sack on your head. Nothing happens till it decomposes. Okay, so that's why urea is an easy form of ammonia for fertilizing. And another very important, these are all other compounds which are not that industrially important. Nitric acid is very important. So nitric acid is ammonia by oxidation over platinum gives nitric oxide. Nitric oxide with further oxygen form nitrogen dioxide. Nitrogen dioxide, if dissolved in water, you get nitric acid. Okay, this is the most well-known industrial process, okay, for making nitric acid. But nowadays there is a new important application of ammonia, that is for making gallium nitride. Okay, so gallium nitride has become a very sought after compound now because this is the material which is used in light emitting diodes or LED bulbs. Nowadays, government of India itself is saying that every family should get 2 LED bulbs free. But when you go to the electricity office and ask, they say stock that is not there in the stock. Okay, but actually you're supposed to get 2 bulbs free because the amount of power consumption in a LED bulb and the longevity or how long it lasts is much more for LED bulbs. And the whole technology, which is entirely different from the normal bulb or the tube light or anything like that, has come because of the fact that we are able to make gallium nitride. So the makers of the gallium nitride got the Nobel Prize for this. And very soon, all the sources of street lights, your own house light. Nowadays, if you make a new flat, you have to give in writing that all the bulbs which you are using are going to be LED bulbs. So this is again a new industrial product which has become important. So these things are not got into textbooks. That's why I'm telling you this, because urea may be there, nitric acid may be there, ammonia may be there, but gallium nitrate is one of those very sought after compounds in the world right now, just for making white LED bulbs. Okay. The other LED bulb is only for Diwali and Christmas. Okay. Whereas the white LED bulb is your day-to-day life. Okay, now the Fritz Haber also had a very dark side, or the bad side of Fritz Haber. So he is the person who also started the first chemical warfare. So he actually made, those days the wars were made, or during the First World War, Second World War, the trench warfare was there, because the soldiers used to dig trenches and move in these trenches. So the problem is soldiers moving in the trench is that they cannot be easily killed. They can sit down, and if you're shooting with a gun, you cannot shoot down, you have to shoot straight. Even if a tank is moving over there, they will sit there, they won't get affected. So it was very difficult to fight people who are in trenches. So, but Fritz Haber, whose belief was that during peacetime you should do research. During wartime, we should become a soldier. So he found out a way. He said that if you take chlorine cylinders of chlorine gas, and open it up near the trenches, chlorine being a very dense gas will go down the trench because its density is higher. And those soldiers who are hiding in these trenches can be killed. And he tried it on the soldiers. He went with 5,000 cylinders of chlorine and killed. Remember, this is the same person. He was called Dr. Evil after that. The same person, is a picture of Fritz Haber with Einstein. Okay. So Fritz Haber is a person who made ammonia and got a Nobel Prize. The same person used chlorine gas to kill people. And his wife was Clara Immerwahr, who was the first PhD in chemistry from Germany. And she told Fritz Haber that I don't approve of your way of using chemistry for killing people. She said, chemistry is only used for the good of people. It cannot use for killing people. As usual, whatever the wife says, the husband will not listen. Okay. And he again continued with his chlorine cylinders and killing people. So Clara Immerwahr did is, by the time the German army had given him uniform and also a pistol as a personal arm, and he once this guy went to kill the people with chlorine cylinders, Clara Immerwahr took this pistol, went to the garden and shot herself and killed herself. Okay, and even then he had no remorse, this man. But the humanity now remembers Clara Immerwahr because she is one of the very first people who talked against using chemistry for war. You should not use chemicals for war. So now chemical warfare agents are banned all over the world, but still some of the rogue countries like Syria and all still use chemical warfare agents. But you should know that these are two different phases of one person who made a chemical with which the whole world could survive, and another chemical with which he can kill. In fact, during Second World War, killing of the Nazis, it was said that cyanide was being used for killing Jews. And again, Fritz Haber had contribution in that. So this is what I say, that that's why British, the BBC came out with the term that bread from heaven and gold from sea, because he also came out with an idea that you can actually concentrate gold from seawater. He was a very, very ingenious scientist. Okay, but only thing is he also had this bad problem. Okay, so this such sort of stories will get people enthralled. Otherwise, what is Haber process? N2 plus 3S2 giving 2NH3. Okay, that is an equation to mug up. So instead of mugging up that equation, if you know there is so much of history behind this one equation, students will get interested. Okay, that is the way I have been doing it. Okay, nitric acid. Okay, as I said, oxidizing ammonia gives nitric acid. Nitric acid is the material or the nitrating mixture. Ammonia, nitric acid, sulfuric acid is used for making almost all the explosives. Here, for example, RDX is there. Okay, and here, for example, TNT is there. Okay. Then this is nitroglycerine, and that's again a very important ammonium nitrate. Ammonium nitrate is a very notorious compound now. I'll briefly mention about that. So, for example, ammonium nitrate, this has come in the news very recently. So ammonium nitrate, if you normally heat it, okay, at 170 to 280 degrees centigrade, it gives nitrous oxide and water. This is what is given in the standard textbooks. But if you heat ammonium nitrate, suddenly it gives N2O2 and H2O. So it's called as a secondary explosive. Okay. This is what is known as a secondary explosive. So ammonium nitrate explosion has happened long time back in Texas City in 1947, where two ships were having ammonium nitrate, and fire started and it exploded. It actually, they said that even aeroplanes which are flying in the sky fell down because of that. And very recently, if you have been watching the news, 2020, there was an explosion in Beirut City, where ammonium nitrate was stored in the port and it exploded. And because there were some fireworks also kept along with that. So ammonium nitrate is a compound. For example, this is classic case of a fertilizer, because ammonium nitrate is also one of the very well-known fertilizers to be used, which has been in the market, which you can use it. So it's an explosive fertilizer. Okay. And so there are a lot of such nitrogen compounds that are explosive. Azide, okay, azide is what is used in car. I mean, for protecting the driver, there is a balloon which will come between with the steering wheel and the driver, that is having azide in it. Okay, pentazenium, the polynitrogen compounds, pentazolate, which came in 2017. These are all high nitrogen compounds, compounds having a large number of hydrogen atoms, and when you heat it, they explode, giving an N triple bond N. Okay, now I have about 2 years back written an article called "The Explosive Chemistry of Nitrogen" in this chemical education journal, Resonance. It is also freely available on the internet. You can download it and read it. It will show very fascinating stories on the chemistry of nitrogen, the explosive chemistry of nitrogen, how over the years people have found out this property of nitrogen, and stories associated with that. Why I talk about all these stories? Okay, you go to a class, okay, and you want to teach something which is terribly boring. You tell a story, a real life story, the students gets interested. Okay, so that is very important, because and these are not made up stories; these are real stories. Okay, how was the explosive property of nitrogen discovered? Okay, how was it discovered that the nitrating mixture is having this useful property of nitrating? Okay, all these are very interesting, and everything is there in this article. You can always download it and read it. Okay, now I hope I have a little more time, right? How much time I have more?
Yes, sir. You can take another 10 to 15 minutes.
Okay, yeah, because I'll try to finish in 15 minutes. So now let me talk about oxygen. So nowadays oxygen is very important, and now Kerala is suffering from COVID. Is in Kerala, okay. And one of the things which you require if you are suspected of COVID is that you should have this pulse oximeter. Okay, it is fitted on or just have to, like a clip, you have to keep it on your finger and read out how much oxygen is there in your blood. And 98 is a good number, 96 is a good number. If it goes below 90, then you need to be hospitalized. Okay. So that is why this has become a very useful equipment during. So it actually reads out the blood oxygen saturation, or the peripheral capillary oxygen saturation. So oxygen has become extremely important now, and in Delhi, now it's slightly better. Earlier, when things were bad, the government used to send your home oxygen cylinders so that you don't have to go to hospital. You can take your oxygen in the home itself. Okay. Especially young people don't have to worry about it. People above the age of 60 definitely have to worry about COVID and take enough precautions on that one. Okay, so oxygen constitutes 20% of the 20.94% of the Earth's atmosphere, and its only allotrope ozone constitutes 0.6 ppm allotrope. So this is liquid oxygen, this is liquid ozone. Okay, so both are blue colored. This is a little more darker blue in color. And oxygen, so everybody knows about hemoglobin and myoglobin, and how oxygen is carried by hemoglobin from the lungs to the muscles. All bioinorganic chemistry you have learned. Okay, so there is nothing new about it. But industrially, 25% of the oxygen is used for the making of ethylene oxide, which is again further converted to ethylene glycol. Ethylene glycol is this what is called the antifreeze or coolant. This is there in all the vehicles nowadays. Other uses of oxygen include medical use for oxyacetylene flames, welding, and liquid rocket fuel. And you know that plants produce oxygen during photosynthesis. Yeah, now more than 50% of the industrial production of oxygen is used in what is known as production of iron ore and steel, because you have to have a air blast here or a oxygen blast here. That oxygen will react with carbon because you also coke here, and from carbon dioxide react with further carbon, forming carbon monoxide. And this is carbon monoxide which reduces the iron ore or the ferric oxide to metallic iron. And so always remember that whenever these are typical NCERT 12th standard chemistry, okay, what is the actual role of oxygen? Oxygen is used for making carbon monoxide, and carbon monoxide is the thing which actually reduces the iron oxide. And then again, the ozone is extremely important for the protection of the human beings from ultraviolet rays. So there are 3 different types of UV radiation: UVA, UVB, and UVC. And the ozone layer is able to protect or absorb the UVC and UVB, and UVA is relatively harmless. And so that's why it has become very important that we should not give to the atmosphere compounds which destroy the ozone layer. That is again one part of the fluorine chemistry. Okay, now these are, as I mentioned, the industrial use of oxygen in smelting of iron ore, and this is called ethylene oxide, which is again used for making ethylene glycol. And then the other applications in hospitals and in oxyacetylene flame. But what is very important as far as the oxygen chemistry is concerned, this little bit of biochemistry, which is normally not taught in colleges and schools. And this is extremely important equation. Okay, and that's why I wanted to mention here. So what happens to the food which we eat? Okay. Why do we eat food? Okay, for that matter. Now, why do we breathe? A very simple question which students ask you. Okay, and the whole thing can be explained by this particular equation called the oxidative phosphorylation. Okay, so the oxidative phosphorylation is glucose. Glucose is one of the example here. Glucose in the presence of oxygen and ADP is adenosine diphosphate, and acid H plus is converted to carbon dioxide and water. And adenosine diphosphate is converted to adenosine triphosphate. Okay, so basically what you see here is that energy. Okay, so ATP is known as the universal currency of energy. When I lift my hand like this, because I have ATP produced in my body, I am able to do it. So when glucose is converted to carbon dioxide and water in the presence of oxygen, that is why we breathe. Okay. Because breathing, you know, it goes to the lungs. From lungs, it goes to the muscle. What is happening in the muscle? So this is what happens. This is a very important equation called the oxidative phosphorylation. And where does it happen? It happens in this units called the mitochondria, which is there in the cells. Okay, so the powerhouses of the cells are the mitochondria. And in the mitochondrion, then ATP is produced, and ATP is then used, and there are about 5 grams of ATP in the entire human body, but up to 40 kilogram equivalent of ATP is used in 24 hours. In human beings, ATP molecules are recycled up to 750 times per day. So much of ATP is produced in our body. And very interesting aspect of this whole, who discovered ATP? Okay. And many people don't know that a name Yellapragada Subbarao. Okay, he was an Indian American. He was an Indian medical doctor from Madras who went to United States, worked in Harvard Medical School. He was involved in the discovery of ATP, but he never got the Nobel Prize because those days the Second World War was going on, and so the ATP synthesis is something which never got the Nobel Prize. And people don't know about this Rao. People all know about another Rao, CNR Rao. But compared to CNR Rao, the contribution of this man is too good, because in medicinal chemistry also he had made many drug molecules. A drug for elephantiasis. Okay, that means legs becoming big due to some microorganisms. Then even there are many discoveries of Subbarao, and this is one of those classic cases. So you should remember that if there was no oxygen, then you should get only 1/18 of the energy which a glucose molecule would give. But when the oxidation happens in the presence of oxygen, you get more. Or rather only 2 ATP molecules can be made, whereas if we have oxygen, you get 36 ATP molecules made. That is how the whole story is there. I could have shown a video, but unfortunately, I am short of time also. Maybe some other time I can do it. Okay, now briefly about fluorine and chlorine, and then I'll close it. Fluorine is one of the most reactive elements and one which having the maximum application. So when you describe fluorine, this picture is very relevant. It is an angry woman with fire on the hair. That's what they say about fluorine. An angry woman. Angry woman itself is very difficult to deal with. If there is fire on the hair, it is even more difficult to deal with. So it is almost impossible to handle this element called fluorine. Okay. With all due respect to women, I had to make this statement that that reactivity. So because problem is, how do you even store fluorine gas? That's why India, very few places you see fluorine research is going on. So fluorine has many industrial applications, important applications. Okay, but handling fluorine is extremely important. You need special vacuum lines which are made of metal. You cannot use glassware for that. You need special metallic glasswares, metallic reaction units for what is known as vacuum lines for handling that, etc. And reactions carried out in steel bombs like this, which are actually passivated with fluorine earlier. Okay, so fluorine have very interesting properties: high electronegativity, small size, highest standard ox potential, natural abundance, and again the carbon fluorine bonds, which are the organofluorine compounds, have very interesting applications, like strongest among the carbon halogen bonds, highly polarized due to electronegativity difference, and then high volatility. That is where they are used as refrigerants, because the fluorine is so electronegative that it will not share its electron density to other elements. So that's why secondary interaction, like hydrogen bonding or weak interaction with other molecules, almost is it is not present in organofluorine compound, especially small molecules. Okay, and another very interesting property is it is resistant to carbon fluorine bond, is resistant to biological oxidation. So if you learn bioinorganic chemistry, you might have come across an enzyme called cytochrome P450. Cytochrome P450 converts a CH bond to a COH bond. That's how many compounds which are not necessary in our food are being decomposed by cytochrome P450 and removed from the body by making it polar. But if you have CF bond, it doesn't get polarized. So this is the reason why it is put in many drug molecules. Maybe some other time I can talk about that. There's a lot of interesting applications. Please read my book for more details. So fluorine has this unusual property that it reacts with any element. Okay, all sort of elements it reacts. And in fact, only very recently they found that even fluorine occurs free in nature. That is inside some crystals of calcium fluoride or fluorite. Fluorite is calcium fluoride, where it was found to be trapped over billions of years. So otherwise, people thought that fluorine is so reactive, it will not be naturally available. Now, one of the very important places where we encounter fluorine every day is when you brush your teeth. Okay, and there's a lot of interest. There is an interesting story behind this also. So this central picture is what everybody, especially girls, like to have. Okay, what is known as the normal pearly white teeth. Okay. But if you don't brush your teeth will be like this on the left side, dental caries. And how fluoride gets added into toothpaste is based on a discovery of a young dentist called Frederick Mackay when he was practicing as a dentist in Colorado Springs, USA. When he came to Colorado Springs, USA, he found that all the people, young and old, in the city of Colorado are having this brown stained teeth. Okay, whenever they smile, you can see brown teeth, not the pearly white. Okay, but surprisingly, he also noticed that very hardly anybody is having dental caries or tooth decay. So this, being a dentist, it really confused him. How come nobody having any dental problem or dental decay? Even small children otherwise will have dental decay. Oh, those is 1901. Okay, then he found out that the water, the well water or the drinking water available in Colorado Springs has a good amount of fluoride in it. Okay, so they analyzed for all the ingredients in the water. They found there is excessive fluoride content in the local well water. And then later on the studies was found that if you keep below 1.5 ppm the fluoride in water, then you won't get dental caries. Okay. Whereas if it is there, of course, if it is in slight excess, this is one of the issues which you have. Okay. There are other issues also that I am coming to that later. Okay. So, but what the issue is that, so this is basically what I mentioned, hydroxyapatite will, in the presence of fluoride, will get fluorapatite. So hydroxyapatite is easily attacked by acids which are produced in your mouth, whereas fluorapatite is not affected by acid. That's why the toothpaste actually converts part of the hydroxyapatite to fluorapatite. And there are many additives like sodium fluoride, stannous fluoride, sodium monofluorophosphate, which are added. Now the problem is that if the amount of fluoride in the water is above 1.5 ppm, then there's a problem. That's what is seen in this kid. If you look at the legs of these children, you can see they are all bent. In fact, you can see it even worse in India. This is called the Nalgonda district in Andhra Pradesh. Okay, you can see that people, especially the lower part, tibia bone, okay, is bent. It is so much bent, this lady cannot even walk. And if you go to these villages, and you can see that this is very much prevalent. And if you analyze the water there, you can see that 17 out of the 21 districts have fluorosis. So fluorosis means too much of fluoride in the water. And then something very interesting is there that if you look at the whole of India, there are many states like Delhi, Haryana, Punjab, UP, the cow belt, you normally call it, okay. And Andhra Pradesh have more than 1.5 ppm of fluoride in drinking water. This is called the well water, not the tap water, the well water. Kerala also has about 5.4 ppm, but Kerala has much less because river water is being used for drinking water, okay. So, but the point is that this Haryana, Punjab, UP, except 25, 29, 40 ppm fluoride is there, but you don't see people with legs bent like that there. Okay, this is found only in Nalgonda district of Andhra Pradesh or in a few such places and among the poor people. So then there's a very interesting correlation was found. That is what interesting about fluoride chemistry. These people in the Haryana, Punjab, etc., they drink a lot of milk and milk products. Okay. In IT Delhi, if you have Punjabi students are there, their lunch is 2 packets of milk. Okay. You can go to the shop and buy 2 packets of milk and they drink it. So, you know, but poor people cannot afford to buy milk. Okay. And if you don't drink milk, so what is the relation between milk and the fluoride? So if the drinking water is having fluoride, if you're taking calcium in the soluble form, what happens is that that soluble calcium reacts with fluoride, forming calcium fluoride. Calcium fluoride has a very low solubility. So it just gets excreted from the body. And so the fluoride is not affecting the bones of the people who are exposed to high amount of fluoride in drinking water. Now, why is the lower part of the leg bending? Because the whole body's weight is actually supported by the lower limb, the tibia bones. Okay, so because it cannot take the weight, it starts bending. Okay, so and because that's why this is called the osteoporosis, because this equilibrium, calcium goes inside the body and comes out. Okay. All that the fluoride is affected by the fluoride because fluoride will take away the soluble form of calcium. But if you are taking milk, then you see that this effect is not there. So that's a very interesting observation in India. So the take-home message here is that you don't avoid groundwater for cooking and drinking. And if you are drinking tea, you drink tea with milk. and eat always, drink a lot of milk and milk products. That is extremely good because it's a soluble form of calcium. So the fluoride issue can be handled even by taking calcium. Okay. Now the last element which I want, a few minutes I want to spend is based on a quiz. Which are the 3 time tested and simple chemicals which have stood up to help the humanity to get protected from infection by the coronavirus? Can anybody say? Simple chemicals which have come to the help of humanity right now. Number 1 is soap. Okay, wash your hand with soap and water. Number 2 is alcohol. Isopropyl alcohol and ethyl alcohol in 70% is the ingredient, should be the ingredient in a sanitizer. Number 3 is chlorine-based chemicals, which are actually disinfectants. So chlorine has a very important role to play about in disinfection. That's what I would like to mention. So these are some of the properties of chlorine. Even what they say is that when bacteria gets inside the they are actually attacked by the gastric juices, and the gastric juice is having hypochlorous acid because hydrogen peroxide is produced and hypochlorous acid also is produced. So even inside our cells, hypochlorous acid is produced. Okay, so among all the halogens, you can see the maximum produced is chlorine. Okay, so where is all this chlorine going? 40% goes into PVC, 18% goes into isocyanates and oxygenates, and these are especially important for making polyurethane. What is polyurethane? Polyurethanes are forms, okay, the rigid form and flexible form. The mattress on which you sleep, if it's not a cotton mattress, it is made of polyurethane. Okay, so and there are many other applications. So this chlorine is made by the chloralkali process, which you have learned. I'm not going to go into lack of time. There's some of the industrial use of chlorine. You can see that polyvinyl chloride. This is made by chlorination of ethylene, and methyl chloride, chlorination of methane, that is used for silicones, as I mentioned earlier. And epichlorohydrin is used for making epoxy resins, okay, araldite and etc. And these are diols and diisocyanates. Okay, diols and diisocyanates. These are what are used for making polyurethanes, which are actually sponges or rigid insulators. Of course, chlorine chemistry again is related to another very interesting observation, that chlorine free radicals. So this one is the free radical chemistry in the presence of UV radiation. Chlorofluorocarbons give chlorine free radicals. They actually react with ozone, converting it to O2. And again, the chlorine free radical regenerated, that keeps on destroying more ozone. That is the ozone depletion happened. Okay. So I wanted to tell that this free radical chemistry is very much prevalent in the chlorine. Yeah. And that is why it is one of the in chemistry also. If you identify the free radical chemistry, it becomes a very interesting aspect. I will skip a few slides here and then go further. Now, these are some of the disinfectants which we come across. Sodium hypochlorite is a bleach. Okay, calcium hypochlorite is bleaching powder. Parachlorometaxylenol, that is what is there in Dettol. Benzalkonium chloride is there in Lysol. Savlon or chlorhexidine is there in Savlon, and chlorine dioxide, which is actually used for purifying water these days, and trichloroisocyanuric acid. This is what is as a chlorine tablet, which actually decomposes to chlorine gas, especially for cleaning or disinfecting swimming pools, etc. Now, the story, this is the last story I have to say. This is the story of Ignaz Semmelweis. Okay, so, and all this story and chemistry is coming out as an article which is coming out just now, this month. Next week, it is going to come out in Resonance, Journal of Science Education, written by myself and my former student, Chlorine and the Chemistry of Disinfectants. So this have all the stories, but I'm just saying one story from that here. This Ignaz Semmelweis, he was actually a doctor or a supervisor in a hospital in Vienna, and he found out that in hospital, when young mothers are brought in for childbirth, many of them die. And one very unusual observation he saw that was there are 2 wards there. One ward was manned by doctors and house surgeons. Other ward was managed by midwives. But the maximum death of young mothers happened in the ward managed by doctors and house surgeons. He could not believe it, because doctors are supposed to be experts. Then he saw something. He saw that these doctors are also practicing their surgery on dead bodies in another room. And when a patient comes, they come and attend to the patient. And he realized that these doctors are carrying something from these cadavers, which they were actually disinfecting and carrying it to the patients. So he suggested that all doctors should wash their hands with chlorine water or bleaching powder, chlorinated lime, it's called bleaching powder. And by doing this one simple act, he could actually bring down the death of young mothers. And that is why he's called the savior of mothers. It's a statue of Semmelweis in Budapest. In front of St. Ruckus Hospital, you can see mothers and children here in the statue. And even this university is now called the Semmelweis University. But see, so mothers are dying. He said that there is, you should wash their chlorine hand wash was strictly requested. But what happened was that the doctors of that time said, this is nonsense. How can you actually get rid of diseases by simply washing? So they said it is not, it cannot be that simple. So they said, this all nonsense. So the death is due to many other things. And he became very angry. He wrote to all the European obstetricians that you are all irresponsible murderers. And then they thought that this fellow is mad, and they put him in a mental asylum at the age of 47, and he died there, okay, because beaten by the guards because when he tried to escape. So now later on, this was a time when even the germ theory was not there. But he was a very keen observer. He observed that there is something happening here, and he had a remedy for that, okay. And so later on, when the germ theory came out, they found that what he said was right. From the dead bodies, they were carrying some germs to the actual patients and transporting that. That is why washing of hands became extremely important. That's why even now, during the corona times, we are asked to wash our hands with soap water or using sodium hypochlorite for disinfecting. Okay. So to conclude, so what should be the most desirable quality needed to become a good chemist? So whenever you write practicals in colleges and schools, you say experiment, observation, and inference. Okay. So this observation is very important. Okay. A good chemist should be a keen observer with the eyes of an eagle who can see the minutest changes happening around and in his her reactions. So a keen observer is a good chemist. Okay, eyes of an eagle you should be having. So, and then Justus von Liebig, whom we mentioned earlier, he said that observation is like a piece of glass, which as a mirror must be very smooth and must be very carefully polished in order that it may reflect the image pure and undistorted. So observation, keen observation, that is what will make a good chemist. Chemists need to observe. So Semmelweis observed that the doctors are carrying something from the dead bodies to the patients. He had a solution for that. Like that, a good chemist, always see the observation is very important for a good chemist. Okay. So what are the take-home messages of this whole lecture? Learning the chemistry of B-block elements is extremely important. It makes aware of the unique properties of these elements, their compounds and their reactions. And there are real-life applications as bulk chemicals. And then many of the metals are non-toxic compared to Ransome metals. And you can see that the major application comes to synthetic fertilizers like ammonia and phosphates. And they are abundant in nature, earth-abundant compounds. And they are safe environmentally. And the chemistry of semiconductors have making modern life much more comfortable. Chlorine, for example, is a disinfectant to make a disease-free life for human beings. And modern main group chemistry focuses on low-valent compounds, P-block elements, and their properties. Okay. Now, before I conclude, this is something which we are doing in IIT Delhi, with main group chemistry. For example, we are using, very recently, we have published some papers on using simple sodium chloride, common salt, okay, table salt as a catalyst in water for converting, oxidizing alcohols to carboxylic acids or converting heterocyclic methylated N-heterocycles to alkenes and alkene derivatives. All this just now come out. So what I'm showing is that even main group elements are now considered earth-abundant catalysts. So nowadays the research is going into making catalysts which are metal-free. Okay, so when you have for metal-free catalysts, we need main group elements, P-block elements, and they are green and sustainable. So this is what is what is another interesting aspect of research in main group chemistry. Okay, so this is a picture of my research group in IIT Delhi. Thank you for your kind attention. If you have any questions, I am willing to answer that.
Thank you, sir. Thank you
Thank
for
you,
the
sir. Thank you,
very
sir.
interesting session. Actually, you have made us as an eagle to just stare at your presentation. I hope so. Now, every people, if they are not eagle, they will become an eagle against you, regarded to this PBOK element, all those things.
Thank you. The
Yes,
whole
sir.
idea was
Actually,
to tell what is there in people chemistry. How do you make people chemistry learning and teaching interesting? So that's what the idea of this lecture was. Okay.
yes, sir. Actually, you have marked it here, I can say. And first, we will take the questions from the chat box. Then we can ask the people to interact with you for some 2 or 3 we can allow.
Yeah.
So only few questions are there, maybe because everybody is mesmerized because of your very interesting stories. I mean, the history, not a story. It is an history, right? Okay.
History is a story. Okay, so that's why it makes
Yeah.
chemistry interesting. Okay.
Yes, sir. And there's a question from Venkatachalam V. Is there any alternative material available for gallium nitride?
A good question. What I understand is that graphene is being I mean considered. There are many, but as of now, I would say gallium nitride is also a relatively new material. So, see, I don't think there are, as far as producing white light is concerned, there is nothing as of now. Graphene is not for this one. Sorry, graphene is used for indium tin oxide substitute. Okay, for gallium nitride, I don't think there is anything as of now. Or although there is some studies on some nanomaterials going on, but what I have told you all are real life applications right now available. Okay. Research will go in different directions, but what is there in the market right now, the technology which is used in the market is what I have focused on. Okay, but even there is, see, basically, if you read the Nobel lecture of Nakamoto is the person who got the Nobel Prize for this gallium nitride chemistry. He tells how it all got developed. See, actually, there is gallium and indium gallium nitride. So if you take gallium nitride and keep on doping indium, then you can get all the colors of the visible spectrum. And of that, he takes the blue light and then use an additional a cap on top of that so that the white light is coming out. This white light is different from the other white light. But of course, now the new technology has happened again where you mix the 3 colors, okay, blue, green, and what is yellow, okay, and make the visible spectrum similar to the normal color, normal white light. But as of now, to my understanding, nothing of industrial level has not come like gallium nitride. All the LED lights you're having is made of gallium nitride.
Sir, can I move to the next question?
Yeah.
From Nitya Narayanan. If we use excess of alcohol and chlorine, what will be the effect of these in the groundwater and air or human skin?
See, alcohol, I don't know, but see, chlorine, there is one thing you should understand. Okay, pesticides, early pesticides, especially Kasargod, endosulfan. Okay, Kasargod is notorious for endosulfan. Endosulfan is a chlorinated pesticide. DDT is a chlorinated pesticide. BHC is a chlorinated pesticide. These are known as POPs, persistent organic pollutants. Okay, so these compounds actually does not decompose. They go down, get into the groundwater and contaminate the groundwater, and there are many side effects of when you have too much of pesticide in drinking water. Whereas nowadays, this is being replaced by phosphorus-based pesticides. Okay, so the difference between a phosphorus-based pesticide, both are main group anyway, and chlorine-based pesticides, that phosphorus-based pesticides easily decompose under UV radiation. So if you put it on the ground with the UV radiation, they decompose, and what the decomposed product is phosphate, and phosphate is a fertilizer. That's why more earth-abundant, more environmentally friendly and harmless pesticides are phosphorus-based pesticides. And you should know that in all over the world, DDT has been banned except in India. Okay, that is a funny thing about India. In India, still DDT is being produced because DDT was very good for protecting most people from mosquitoes. So we see that still malaria is there in India in some areas, and that is but we have promised that very soon we'll also stop production of DDT. You should learn about, you should read about the about one lady who wrote a book called the Silent Spring. Okay. And she actually is the person who is responsible for banning DDT in the United States, because this DDT was excessively used, and they found that even small birds, small insects, small animals die. And then there are many side effects on human beings also. So DDT was banned. Okay. I forgot her name, but her book's name is The Silent Spring. So if you read The Silent Spring, you will know how it all happened. But the government of India has still not done it. Okay. And hope.
Sir, actually, we have another lecture also.
Yeah,
maybe one more question we can take up.
Last question. Okay.
What are the applications of monovalent silicon compounds?
Yeah, see, this is a research area. And you ask the question which everybody asks, what are the applications? Okay, so I've been talking about all applications in this lecture. Okay, but this is an area which is just now coming up. See, similar to N-heterocyclic carbenes, N-heterocyclic silanes have been made, and they have been found to act as good ligands as catalysts. Okay. In making of catalysts for hydroformylation reaction, hydroboration reaction, all that catalytic activity is there. But this question, what are the applications? Applications always in research, you should remember that it is not application oriented always. It is actually trying to make new compounds, study the property of the compounds, and then when you study the property, then only you realize if it can be put to any use. Okay, but right now, as I said, it is a hot area in research doing low valent main group chemistry, because these are highly sensitive compounds. So as of now, if I say there are a few compounds known as catalysts, that's all.
Yes, and then there are again, now they are posting many questions like any method to eliminate higher fluoride content in well water, or how can we check the quality of fluorine content or arsenic content?
Oh, there are standard methods are there, because even United Nations have a lot of projects in India, and many people have come. There are many methods of doing it. Best way to contact is Professor T. Pradeep in IIT Madras. Okay, he does a lot of work on water purification and non-fluoridation and removal of arsenic, etc. There are standard methods for that. I didn't touch upon that because that is going into a very detailed study. But as I said, the calcium fluoride. Okay, this is one of the things you can remember. Calcium fluoride is one of those very insoluble compounds. So if it is soluble, fluoride can always be made insoluble by adding calcium. That's why I said, if you drink milk, the soluble calcium in the milk actually will precipitate the calcium fluoride. Another thing is that if you have hydrofluoric acid falls on your hand, you can get killed, because hydrofluoric acid goes inside the skin, and then in search of calcium it goes and forms calcium fluoride. Okay. And you die by what is hypocalcemia, because your calcium content in your body comes down. So the antidote for that is calcium gluconate. That is a soluble form of calcium which is injected on the site where the hydrofluoric acid falls. So that calcium, soluble form of calcium, will react with the fluoride and convert it to insoluble calcium fluoride. So any technology which is based on calcium fluoride is well accepted, because calcium fluoride is insoluble. It remains as a precipitate. It can be decanted off.
Yes, sir. I think participants have more questions. Now they are thinking about all the lectures.
Now they can write me email whenever I get time. I will reply. Please check the website for Anil J. Elias. You can get my email ID. Give me an email. I can answer you. If I know the answer, we can answer and give you.
Yeah, we can share the questions, sir. We can share the questions, sir.
Thank you very much.
So,
thank you.
Thank you.
Bye.
Thank you very much, sir. Thank you very much for being with us. And really, everyone has commented that you have mesmerized them because with the history, I hope. Sir, Saktivel sir, shall we move on to the next session? Right, sir?
Yeah. Please proceed. You are sharing. You are the sharing.
Okay, thank you. I am now coming out. Okay?
Thank you.
Yeah.
Yes,
Yeah, thank you, sir. Thank you, Professor Elias,
sir,
for
Elias,
coming, and in a short note you came and given us a wonderful lecture, sir. Thank you.
Thank you, Professor.
Yeah, thank you.
Yes, sir. Thank you, sir. So now I invite the next speaker, Professor Dr. M. Satyendran from University of Hyderabad. He is also one of the expertise in inorganic chemistry field. So he has worked as an assistant professor in University of Delhi. After that, he moved on to University of Hyderabad, and currently now he's a professor in University of Hyderabad. To his credits, he has published more than 60 papers, and which is having the number of citations like around 1,500 approximately. And his H index, everything is very high. It's around 20. So it can be seen that now he's actively involved in the research. So it is very good to have his lecture, we hope. And he has been delivering many lectures all over the world. I hope all over the country, in China, like that. Many countries he has visited, and his research is mostly related to the inorganic materials like aromatic primers, uh, and then what to say is ruthenium based complexes. All those things are there. If you can reach the his site, you can understand the informations. And to add on, he's our co-convener's best friend. So we have to appreciate him for being with us to deliver his research. And he is also doing research on CO2 reduction in order to contribute to the global warming, all those things. So we are very much eagerly waiting for you, sir, to hear something about your expertise here, and I think everybody will be benefited by your lecture. Sir, over to you, sir. Professor Dr. M. Satyendran, sir, you can take the control, sir.
Thank you very much. Before coming, I will ask the MSc student who joined the previous lecture. Please leave this. Okay, this lecture is for not for you. Okay, so I request if anybody, I mean, MSc student from the University of Hyderabad, if you are in the here, please leave the meeting. Okay, thank you very much. So first I will share.
Sir, you have muted, sir. We cannot hear you. Sir, you have muted yourself.
No problem. Just I'm working on it. Okay, just give me 2
okay,
minutes.
sir. I thought you started. Sorry.
Any problem? Is it okay?
Sir, he has muted.
Satyendran?
Yeah, no problem.
Finish.
Yeah, are you able to see?
Yeah.
Are you able to see the slide?
Yes.
Yes, sir.
Yes. Fine.
Thank you so much, particularly the organizing committee and the Department of Chemistry, including Professor Shaktivel and Professor Guru and Professor Kumar and Professor Bhakya Lakshmi and all in the Department of Chemistry for giving me the opportunity to share the teaching which what I encountered during my teaching, in particular the main group chemistry. So I'm not going to teach anything from what I have been doing in my lab. Okay, so I thank all the people, in particular Professor Shaktivel and all the organizing committee for giving me the opportunity. So this is what when I see the topic, it came to my mind. For hundreds will be 100. Okay. You cannot teach the teacher. Okay. If you try to teach this to a teacher, you will be 100. So rather, what I'm thinking, sharing the knowledge or sharing the things which I encountered during the teaching, or some of the things, or some of the articles. Okay, some of the articles which I feel very happy to read, very happy to listen the related things. So I thought I will share that material to you rather than the teaching. Okay, because this slides, of course, you know how this education system came to the systems. The people assemble in the common places and they say what they came, what they think, what they analyze with other people. So they won't teach, just they share. Okay? Some of the pictures I will show you because whenever I feel that pictures, I feel very happy. So that's what I'm going to do. Few of the slides and whatever the slides are, I'm going to show you and display you. I feel very happy. So hope you will also enjoy. Okay. This is one of the very famous one by convention Peter, by convention Sweet, but in reality, atoms and voids. This is the Democracies and the Lucifuses. So they talk about the atoms. Okay. Then if it comes to the Van der Waals, one of the greatest scientists, so he only says uh, all matter displays attractions. Okay, all matter displays attractions. No problem, no matter, any matter. Okay, any matter. We can say even if you bring the gas together, they has to feel some attractions. But all solids and liquids, they will feel attractions. And if you come to his follower, the Fritz London, he also agrees. So all matter display attractions. Then I hope you know this one, Heisenberg. So, he is one of the very young, I can say, scientist. I will not put him either in the physics or in the chemistry. I will say he's a very good scientist. He says position and velocity of an object cannot both be measured exactly at the same time, even in theory also. So follower of Niels Bohr, fantastic chemist. So whenever I see these people, I mean the great scientists, I feel very happy. I hope you also. Then finally I will come to the Buddha. He says, believe nothing, no matter where you read it or who said it, even if I have said it, unless it agrees with your own reason and your own common sense, don't believe anything. So this quote I tell because a teacher has to tell these things to the students, and we can say we have to tell to the student, or we have to tell to everybody, because the student should not believe what is written on the book. Not only student and us also. If there is enough reason, then okay, it's fine. Then we can accept. From these pictures, I'll just go to my topic. Okay, just I put it the topic like this. Let us cooperate chemically via non-covalently. So while giving this topic, so what I mean is compounds, okay, exist because of covalent bond. No matter whether it is sugar or water or dioxygen or dinitrogen, any compound you can take it. Okay, most of the solids and liquids, they exist because of the covalent bond. However, the non-covalent interactions play a crucial role. That's what the key. Okay, those are the slides which I saw, Van der Waals and London Bridge and Heisenberg. So they are all connected to the non-covalent interactions. Okay, so all compounds exist because of the covalent bonding, solids and liquids. But however, non-covalent interactions play a crucial role. So this is what I mean when I put the title, let us cooperate chemically via non-covalent way. So what is non-covalent interaction? What are the non-covalent interactions? The non-covalent interaction between the two molecules, we can say very simply, then they have any type of this interaction or the all interactions. You can say ion-ion interactions ion dipole interactions, dipole interactions, hydrogen bonding interactions, the traditional hydrogen bonding interactions and non-traditional hydrogen bonding interactions, which comes under CH5 interactions, pi interactions. Finally, we comes to the London dispersion forces. Okay, one of the weakest among these all the interactions, among all the non-covalent interactions, one of the weakest interactions is London dispersion force. One of the weakest interaction is London dispersion force. For example, one of the strongest, okay, ion-ion interaction is the strongest one, but hydrogen bonding is medium one. You can see here, it's a non-covalent interactions, okay, but you can see it when it, the ice is floating. The ice is floating, the ice is solid because of the hydrogen bonding interactions. Where you can see the majestic, okay, the beer are standing over it. It can able to test even the Titanic ship also, okay, when it's collectively, okay, though it is a big, but when among all the interactions, the London dispersion interactions, generally we call it van der Waals interaction. It's one of the weakest force that we know very well. Everybody we know very well. So what I'm going to share is some of the few things which I read it, I feel that we can tell like this to the our students. Okay? For example, you take the oil, okay, the hexane, okay, it's made up of only carbon hydrogen, CH, okay, CH bond and CC bond, okay, the surrounding is CH. If there is no London dispersion force, it's not a liquid, okay, you cannot run any machines, any oil-based machines, whether it is a car or aeroplane or any water pumping machines, any machines which is based on the oil, you cannot run. The hexane is liquid, hexane, and so which you can explain only based on the London dispersion force. Okay. Now you can see here a lizard. Okay, one leg is hanging. It always asks, so what is gravitational force? Everything has to come down. No problem. I can stick using my own one leg. This also you can able to explain only London dispersion force. Okay, one of the weakest non-covalent interactions you can explain only based on the London dispersion force. Okay, these two scientists, okay, which they contributed to explain what is London dispersion force. Okay, they are as I already said, they are individually weak. So individually weak and essentially negligible. However, in large molecules, the London dispersion force effects can be of considerable importance in collectively inducing stabilization on the order of tens of kilocalories per mole. So what is final is this is sufficient to markedly influence the physical and the chemical properties of any material. Okay, individually made, individually big, but when it's collectively come, they can able to make the influences of the material properties and the physical properties. Okay. For example, strength is the number we can say. Okay, this is I hope you all the children with Kulliver and Lilliput. Okay, it's the strongest man, but if the number is more, you can able to control. Okay, that is what the main thing. Okay, whenever there is people talk about the non-covalent interactions, they talk about Kulliver and Lilliput. Okay, I hope all the children we all read it somewhere in any medium. It will be translated. Okay? It's the strongest person can be able to control by the weakest, but here the strength is the number. The strength is the number. So similarly, the London dispersion force, though it is a weakest among all the non-covalent interaction, but in collectively, if there are more London dispersion force in the molecule, they can able to stabilize the, they can able to stabilize and give strength to the material. Okay. So for example, I don't know why it is coming like this. You can see this. This is what we teach to the student. Okay, from you can say from 9th, 10th, 11th, 12th, even first year college also we will see. So variation of the boiling point of fluorine, chlorine, bromine, iodine. They are all how to say it's a non-polar molecule. Okay, non-polar or diatomic molecule. Okay, only one molecule. Okay, But you see, when you increase, okay, from the molecular mass, the boiling point also increases. Then you can come to the master gases, okay, noble gases, helium, neon, argon, krypton, xenon. Why the boiling point are increases? What is the reason? Okay, so this also you can able to explain. We will normally explain. We have to explain based on the London dispersion force. Okay, we have to explain based on the only London dispersion force. Then you can come to the boiling point of alkane. The alkane which has the CH, only CH mighty, okay, carbon, carbon, the surroundings only hydrogens, okay. You can also see whenever there is a increase the molecular mass, okay, that means when you add the CH, the CH, the CH, the CH2, then the boiling point also increases. How to explain? We can explain only based on the London dispersion force, because we take any alkene, the interaction between two alkane should be the London dispersion force. Okay, there is no ion-ion, there is no hydrogen bonding interactions, so there is no CH5 interactions. So between the molecule in the alkane, there are only one interaction can exist, that is the London dispersion force. So the boiling point of alkane also can be explained only London dispersion. This you know very well. So now I will come to know. For example, you take this one, neopentane. So what I am going to tell, these are all things we know very well. But what I am going to share, what are the things which I feel very happy to read. That I will come. I will share. That's what I said. I will share few papers which I feel we can read it. Okay, we can read it. We can enjoy. For example, you take neopentane, you take N-pentane, both have the same molecular formula, same molecular weight. But whereas this linear molecule, okay, have highest boiling point compared to the neopentane. So this also can be able to explain the weakest London dispersion force. Okay. Now the question is what is London dispersion force? Very simple. You take any molecule, okay. So any molecule, okay, any molecule, if you take any molecule, so proton neutrons are inside. The only the outermost is electron only. Any element, any molecule, whether it is a gaseous molecule, whether it is a solid or gaseous, any material, my face, my hair, computer, everything, the outer is only electron only. You cannot touch the proton neutron. So only all the whatever you are seeing in the world, okay, the wall, everything, the finger you are seeing, okay, you are touching, electron is can be touched, okay, nothing, okay, you cannot touch it, you cannot touch the proton neutron, okay. So the electrons are outside, okay. When it comes to the, that's what you know very well, okay. When it comes to the hydrocarbon, okay, the electron clouds are outside, okay. What is London dispersion force, okay. Then according to Heisenberg concentrative principle, they won't be, how to say, stationary. They constantly move here and there. Okay, that's what it's the position and momentum of the electrons you cannot identify at the same point. Okay, even in theory also, that's what it is. Okay? It constantly moves here and there. So when it moves over there, then you will create the molecule itself will have the one side. When you have the more electron side in one side, you will have the more electron density, that we tell it how to say partial negative charge, then that side is partial positive charge. So this will induce the neighboring molecule, then you will have the partial positive charge, partial negative charge, then this will have the how to say attractive interactions. That's what the van der Waals as well as London says, every molecule, okay, all will undergo attractions. Okay, this is what the textbook people textbook. This is the example of textbook. This is another textbook. There is absolutely no problem. It tells very clearly. Okay, it explains very clearly. Okay, then there is another textbook. Okay, this is the polarization view. You can see two helium atoms and no polarization. That means completely the symmetrical electron cloud. Symmetrical electron cloud. You can see here subatomic view. But when it comes to here, so one molecule due to the electron cloud fluctuation, one side will be more electron density, the another side will be less electron density. Now this will induce this molecule. Okay, this will induce this molecule, and this will create the again at the symmetrical matching. Okay, that symmetrical pair it will create. Now you will have the positive partial positive charge and partial negative charge. They will have the attraction exactly like this. This is the textbook example. So there is absolutely we teach okay from 8th standard, 9th standard, 10th standard, 11th standard, first year chemistry, even college MSc chemistry also. When you read the supramolecular chemistry course. So what I'm going to do, this is the first paper I'm going to study. Okay. There was while teaching this one of the courses, I saw this paper. Okay, a solution to this person interactions. Okay, this is intermolecular. So this post, this picture is I'm going to share you. Okay, the same thing. Okay, whatever this is the textbook chemistry. Okay, this is the textbook chemistry. They have put it very clearly, but if you don't put it to the color, it's very difficult to understand the concept. Okay, this also the student has to write it properly. They have to put the color, otherwise it's very difficult. White and black student cannot able to understand very clearly. I feel most of the students. Okay, but this article, okay, that's what I said. I will share few papers which I feel very happy, which the chemistry which we know very well. I'm not going to give any new chemistry to you. I'm just sharing the papers, few papers. Okay, the chemistry you know very well. Okay, so this picture I'm going to highlight in the next slide. Now you can see this one. Okay, absolutely. Okay, there are symmetrical electron cloud. Okay, symmetrical electron cloud. Electron has to repel. Okay, this is what I feel. If it tell to the student, they can without any color, they can able to understand very easily. Okay, for example, you have asymmetrical atoms. Okay, asymmetrical atoms. Now the electron has to repel here. That's what it says in the electrostatic repulsion in molecules without electron mobility. There will be an electrostatic repulsion between electron clouds. Okay. When it comes to the B, so the one molecule will undergo the instantaneous dipole, okay, because of the constant moving of the electron density. Now you can see here, the two electrons here move to one side. Okay, then it will become unsymmetrical. Okay, you no need any color to explain to the student. The nucleus is exactly same position. Now, when we have the more electron density, in principle, this side should be less electron density. This side should be a less electron density, and this side should be more electron density. I hope this figure I feel very happy to read it. Okay, that's what I said. And it's very happy to explain. Okay, to the simple London dispersion interaction to the student without any difficulty. Okay. Now this two electron density is more over here. That means this side will be more and this side will be electron density should be less. So you have the more partial negative charge, more electron density here and less electron density here. And this molecule will induce the neighboring molecule, the same principle, but in the complementary way, because this is more electron density, so it needs less electron density here, and this is less electron density, so this molecule, this side, it needs the more electron density, so you will have this attractive London dispersion interaction. So there is absolutely no problem. I'm saying this is absolutely no problem, this one. There's absolutely no problem. This is textbook example. I feel this paper is, I feel it is one of the best paper to explain this London dispersion interaction to the student. Okay. The more important further, this paragraph is very, they wrote it. Okay. This author wrote it very interesting. Okay. You may feel it. Okay. You may have to say, you feel it because one has to have to say. Go in very detail, okay, very detailed. But to go to the detail, you no need that much analysis. You can ask very simple question: whether it is possible to touch the electron, whether it is possible to see the electron, the clouds of electron. Yes, for example, you take any iron rod. What is iron rod? If you touch the iron rod, you are touching the electrons only. The nucleus you cannot touch. Similarly, anything, okay. So this simple thing, after a long time, after reading this only, I just, after reading this paper only, I started to enjoy the electrons. Okay, so I read exactly what he wrote. We often take for granted that molecules can form liquids and solids. We often take for granted that molecules can form liquids and solids. Molecules are wrapped in a negatively charged cloud of electrons that should repel each other and inhibit the formation of condensed gases. Fortunately, all molecules can form attractive electrostatic interactions called, you can go to credit to the van der Waals and the London dispersion forces. Okay, even nonpolar molecules can form temporary instantaneous dipoles. Okay, almost all the, okay, every molecule, the solid and the liquid, every molecule in the solid liquid, no matter, all molecules will undergo London dispersion force, whether it is polar molecule or non-polar molecule. Okay, but all molecule will how to say, will have the London dispersion force, because all molecules are, the outside is nothing but electron cloud. That electron cloud will not stay in one side, it will constantly move. Okay, so that's what he said. Even non-polar molecules can form temporary instantaneous dipoles as a result of random asymmetries in their electron distributions. Okay, like this petrol, why it is a petrol is liquid? Okay, why petrol is liquid? Only you can explain this London dispersion force. Okay, these temporary dipoles trigger the formation of complementary. Okay, the word is very important. Complementary, not exactly, the complementary. If there is more electron density, it will induce in such a way that it needs less electron density over there. This is for complementary. Okay, complementary induced dipoles in adjacent molecules. So the electrostatic attraction between this instantaneous and induced dipole is the basis for weak London dispersion force. I like this paper very much. I hope you people will, you can, I suggest you to read this paper. Only this first paragraph is enough. First paragraph is enough. Okay. So because you know these things very well. I hope you will enjoy this paper. Okay. Then this is the second paper. Again, this paper talks about the London dispersion forces. You can read it later. Okay, it talks how this the chemistry, okay, the research, okay, starts from 1873, where van der Waals thesis defines intermolecular interactions. Then it goes on, how it is coming. Okay. Some of the few examined recently what is going on, though it is a weakest interaction among the non-covalent interactions. Okay. Though it is a weakest, okay, among the non-covalent interactions, when you add more, when you have more strength, okay, for example, my finger I can easily break, but when I have five fingers, I cannot easily, how to say, break. So that's what the London dispersion force play a role, how it contributes. Okay, you can see it here. Carbon-carbon single bond, we normally say 1.54, but they can able to make the carbon-carbon. There is a bond is exist 1.67. For example, this molecule, it is carbon-carbon 1.71. They are a stable molecule. Without this, if the R is hydrogen, it forms only not like this, not carbon-carbon single bond. Okay, because this is a radical. Okay, I do not want to go the mechanism, but what I say is there. This is there is a hydrogen, what is CH, okay. This all are non-polar molecules. The temporary fluctuation, the instantaneous and the induced dipoles. So this number is strength, okay. The strength is the number, okay. There are more, the weakest one, but they stabilize, they give the strength to the molecule, which we cannot be able to, how to say, nature doesn't like to produce the similar kind of molecule. For example, you take carbon-carbon double bond, carbon-carbon single bond is known, carbon-carbon double bond is well known, nature likes. Carbon-carbon triple bond, nature compounds are there. Carbon-carbon double bond O is known very well. But you take in the periodic table the same carbon silicon, you just come to the in the group neighbor, okay, silicon. But silicon double bond is not stable. Silicon triple bond double bond we cannot make. Silicon triple bond we cannot make. Nature doesn't like to make. But because of this weak London dispersion force, now people are able to make absolutely no problem. Okay, this is see, this is silicon, this is even if you go carbon, silicon, germanium, tin, lead, okay, because we read it in the periodic table. When in the group, when you go down, they, how to say, they're reluctant to form double bond, they're reluctant to form triple bond, okay, reluctant to form because the orbital, we say orbital will not match. But if you read the main group chemistry, you will say what is bonding man. You can make anything if you design it properly. Okay. So these papers, okay, this paper talks about the complete, okay, the complete story of how the London dispersion force in the molecule helps to stabilize the impossible molecule. Okay, impossible molecule. Okay, impossible. You can read it. These are the examples. Okay, okay. Then I will come to the not new thing. One of the well-known things. Okay, these are all the how to say clatrate. You know the clatrate where the xenon is in the cage. Okay, xenon in the cage. But xenon is non-polar molecule, a single monoatomic molecule. They have to interact. They want to stabilize, they have to interact in the case. Some of them, how to say London dispersion interaction, no other way. Okay. Now, okay. Okay. This is the paper number 3, which I am going to share with you. Okay. This, how to say, the most beautiful, the one page paper. Okay. If you read it, you will really enjoy. You will read it, you will really enjoy. Okay. His name is this, okay, Bartlett. Okay. So a beautiful chemist who, how to say, break the rule. Okay, who break the rule. Okay, he break the rule. Okay, he says nobody is noble. Okay, that's what he is. His chemistry. If you read it, you can put it like this. In the element, okay, element, okay, the element among the 118 element currently, no element is noble element. The noble means the people, how to say, the element will not interact with anybody. Okay, but he is the father of, you can say, the founder of noble chemistry. I think this paper you can able to, if you read it, you will really enjoy. Okay. For example, this is the periodic table. You can see helium, neon, argon, krypton, xenon, radon, organelle. Okay. Most of the bonding chemistry we will say if you have the 8 electron octet rule, especially main group and the alkaline earth metal, if you have the 18 electron, 8 electron, the element will attain octet, then it will not react. Okay. So that's what all the ordinary chemistry, all the chemistry we believe that the noble gases, okay, noble gases doesn't want to interact with anybody. This noble gases wants to be like free, okay. That's why it's called noble. Okay, noble people will not interact with anybody. Okay? But this guy, okay, this guy break that one. Okay, no, there is no noble. Okay, that's what he said. I feel okay, and the most important thing is, and he's from the just how to say University of British Columbia, Canada, where he did that experiment. Okay, this is what apparatus. That okay, who break, there is no noble gas. The apparatus is so beautiful apparatus. Okay, you can see here. Actually, this is how to say. This is the iron bar. Okay, this is the magnetic bar, iron bar. There is a small here. Okay, you can nothing is there is a cross here because if you add any gas or liquid or solid, it will not come in there. They have to break this one. There is a small nap is there. Okay, they have to nap. So what he did, he devised this experiment. See why I'm saying some of the things they cleverly designed with the simple things. And he took the outside. Okay, if it is this is a magnet or iron rod, then he took outside the magnet. If you consider this is a iron rod, he took a magnet. If you move it, you can bring this magnet rod upper. Then if you leave it, it will break automatically. Then the whatever the gas or liquid, it will go and mix this one. That is what is his experiment. Okay, this is what he did. Okay, one side he took the something. Okay, platinum hexafluoride. Okay, this is the platinum hexafluoride. The another is xenon, and okay, this is just if you break it, then it forms a first noble gas compound. Okay, just a simple mixing. People believe that the noble gases are and it will not form any compound with any element, okay? Any element or any compound. But this is a beautiful experiment, okay? So what? So I said I'm not going to teach anything, but I will share it, okay? So this experiment is one of the, okay, uh, this chemical engineering is, okay, one of the 10 most beautiful experiments in the history of chemistry, okay? I don't know what about the other 9, but I feel I agree with the chemistry, chemical and engineering is as one of the 10 most beautiful experiments in the history of chemistry, and one of the most important developments, okay? One of the most important developments in inorganic chemistry in modern times. And what he says, okay, this is what his first paper, and this could, okay, I don't want to even change, okay, the letters, okay, the words, because words have meaning, okay. I read it as such. The crucial experiment happened on March 23, 1962. It was a Friday, and the apparatus was brought together by 7 p.m. These two graduate students both had left at this hour, as they lived in a student residency where dinner was served at 6:30 p.m. Okay, these two graduate students are left to the dinner. So the scientist was all alone in the lab. He broke the seal between platinum hexafluoride and xenon, and there was an immediate reaction because you can visible the red color and colorless cap. You can see the yellow color. He saw the yellow color. I feel that I was doing that experiment, okay? That's what they write. So he was all alone in the lab. He broke the seal between platinum hexafluoride and xenon. And there was an immediate reaction. He separately wanted to tell somebody or anybody about it. You went out into the corridor, but there was not a soul in the whole building. Everybody went to dinner, okay? So he went back to the lab, and suddenly he was floated with the doubts. Maybe xenon was impure. Maybe there was some oxygen present. Me, I'm just fooling myself. Both the urge to communicate about his experiment and the doubt seems to be typical in such a moment of discovery. This is the first experiment done by him, okay, at Friday night, 6:30 p.m. I hope if you read this one, how you can hate the xenon chemistry. But if you read the book, that's all. We will go hell. Xenon will fluoride, it will form difluoride, trifluoride, this oxygen, that oxygen, and this antimony fluoride, that. So you will go hell. But this is the first experiment. I hope if the student read this paper, they feel, I think, they feel happy to know this. That's what I'm sharing with you, okay? I'm not teaching any chemistry with you because then I will be hunted by you, okay? Okay, this is what that experiment. I hope you know very well how he did this experiment, okay? It's only comparison, okay? When you analyze that, the reduction potential of oxygen is very close to this one, then one, if oxygen can able to, how to say, the fluorine hexafluoride can able to remove electron, why not xenon? That's what, this is what the textbook. So this is the color, okay? I hope this I will not go, then that's all, okay? So after few months, okay, this is after few months, okay, you can see there is another chemistry, okay. So all know in the periodic table, you can, if you see the periodic table, that's the chemistry, okay. That's a beautiful, okay. You can say this is metallic, non-metallic, alkaline earth, alkali metal, transition metal, lanthanide, actinide. If you see over there, okay, oxygen is gas, fluorine is gas. But if you go down, then it will be solid. But only the noble gases. We call it in the periodic table noble gases. They are only gases, okay? All noble gases, helium, neon, argon, krypton, xenon, radon. Argon is one or two atoms only, maybe 10 atoms, maybe they have synthesized, okay? But they are all are all gases in the group, okay? All are all gases in the group. But you know, when you coaxed, when you reacted with the you see the beautiful solid color, okay? This xenon fluoride, beautiful, okay? You can see because if you see normally you won't enjoy, okay? All noble gases are gases, okay? Gases, it's unreactive gases. People believe that all the elements, if you attain the noble gas configuration, that's what we put it after to noble gas configuration, then they are stable. We cannot react. Okay, but you see here, beautiful solid. Okay, okay, this is done by this chemist. Okay, this done by this chemist after a few months. Okay, but he did it very simply. This is on the terrace. Okay, you take this is photochemical synthesis of xenon fluoride on the top of the terrace. Okay, you can read everything. You will get all the knowledge, all this experiment from this. This is this special issue. Okay, dedicated to this protocol. Okay, uh, this is what the experiment. Okay. Okay, one of the most elegant synthesis of xenon fluoride yielding a pure product is a photochemical reaction of gaseous mixture of xenon and fluorine with the excess of xenon. The reaction can be performed in the Pyrex flask. The mixture is exposed to direct sunlight or to UV light from a mercury lamp. Very pure xenon fluoride in a greater quantity up to 1 kg. Up to 1 kg can be best prepared by the UV radiation of xenon. Okay, fluorine gases mixes in the mold. Okay, this is you can prepare really. Okay, just put the sunlight. These are all the crystals in the glass. You can see these are the crystals. These are all the crystals. So similarly, the chemistry goes on. Okay, the noble gases slowly loses its nobility. It reacts with other element, it forms the compound. Okay, you can see it here. Okay, xenon is there, krypton is there. Okay, then krypton is there, even argon is. Okay, so this is the timeline. Okay, what are the new noble gas elements are found. Okay. Okay. Then I will share the another paper. Okay, interesting paper. Okay, these are all the, if you go to this natural chemistry, there was a in your element. There is a one-page report about every element, its stories and its importance, everything it will be condensed there. Okay, very nice way, so that everybody feel very happy to read. Okay, you in your element. Again, the nature chemistry, almost most of the element they put it. Okay, and this I'll tell about what is written in this one. Okay, you can see it here. Xenon is there, krypton is there, argon is there. Okay, xenon, krypton, argon. Okay, then there is a this argon chemistry. This why I'm sharing, because in the previous also uh, this one, okay, his two graduate students both had left at this hour as they lived in a student residency where dinner was served at 3 p.m. That means he did alone. Okay, normally student pulls our like some of the scientists pull the student like also. That's what I want to say. You see this common. Okay, first argon common. Okay, first argon common. What is okay? You can read it here. So improper handling of the reactive precursor culture. Okay, you are adding culture to the organ. The first signal of this new species were obtained in my group. Who wrote this article? Okay, the Marco. Okay, 21st December 1999. A time of year conducive to experimentation with no interfering student. He also put the student with no interfering student present in the lab. He did alone. Okay, conclusive experimental results were obtained from the, just I'm for joking, I'm telling you, but the compound is very important compound. This is the first argon compound. A neutral molecule containing argon, I will not have received by a better Christmas present. Okay, so finally, the argon also loses nobility. Okay, finally, argon. Okay, you have a compound with xenon, krypton, argon, neon, and there was a only one element. Okay, that element is the helium element. Okay, that was retains its nobility. That means it won't react with anybody. It won't react with anybody. It likes to be alone. Okay, that is only few years. Okay, then I will show some of the common. Okay, so this is highly explosive. Okay, but we all very well know in the textbook chemistry xenon oxides. Okay, xenon oxides. Okay, then xenon can able to form different oxides. Okay, they are all unstable. Okay, most of the xenon fluoride they are all unstable. But what is more important is they are all how to say. I can read it. Okay, these xenon oxides are crystalline powder. Okay, perlatron were first to experimentally verify this prediction when the white crystalline powder that had been isolated as the product resulting from the hydrolysis of xenon detonator. The event unfortunately resulted in the hospitalization of both researchers. Okay, the xenon trioxide, the first xenon oxide to have been synthesized and structurally characterized. The colorless solid is very telefusion and highly shock and temperature sensitive. This xenon highly shock and temperature sensitive, releasing bursts of energy at the slightest provocation. Okay. So when they do this one, the event unfortunately resulted in the hospitalization of both researchers. Okay. So just I am saying, I am not teaching at all anything. Okay, whatever the paper I feel I can able to, I thought I should share with you. Okay. Okay. So when you see the crystal structure, okay, this is solid state structure of xenon oxide. You can see it here. Okay, there is a xenon oxide and the oxygen. There was a the distance is very close. They say there is a interaction, non-covalent interaction between this one oxygen to xenon, oxygen to xenon. So they say that the interaction is aerogen bonding interactions and use from molecular force. The favorable non-covalent interaction between a covalently bonded atom of group 18, known as noble gases or aerogens, and a negative side, for example, lone pair of Lewis pair or anion. So these interactions they are calling. They say you can simply say there is a non-covalent interaction between the crystal structure says. Again, the molecule they have to come together and they should have some interactions, weak non-covalent interaction. Then only the more atom or more atom you can able to get the solids. So this is nothing but we no need to worry about this bonding. But what I want to say is there is a interaction. Okay, there is interaction. Now the confusion comes. So whenever we first introduce the periodic table, we say all noble gases are gases. They are noble. They won't react. Now we are talking about this. How to say? So many compounds with this thing. Even we talk about there is a non-covalent interaction between the xenon oxide. So I think this. I feel that student. That's what I put it. Saying first not reactive and to be aligned. Now looks interact everything. Okay. So new when chemistry is coming, so all the existing knowledge what we say will disappear. Okay. Now I will tell you. Okay. So in the this is what I said. In the solid state, readily detonates when substituted. Okay, the shock sensitive. Okay, but there was here one reason. Okay, I think this in Tamil Nadu it was very famous. Okay, taming the bull. Okay, taming the bull. Very you have it too horn. Okay, if there is a how to say, if this person okay, if there is a if you miscalculate that's all, this will go to belly. Okay, anyway, there are very highly energetic ones. Okay, highly energetic ones, but still they are well trained. They are well trained. They know how to tam this one. Okay, so that's what the scientists also did. Okay, what they did, the xenon oxide. Okay, the xenon oxide they can able to interact with another oxygen in the solid state. So what they did, they can able to add the another acetonite, the Lewis base. Okay, you have a lone pair over there. Instead of oxygen, they can able to add this one. But this adduct, okay, this adduct, okay, then even they can able to add this crown ether. Okay, this crown ether you have the oxygen, oxygen, oxygen. Then this have the interaction with the xenon oxide. They are perfectly stable. Okay, xenon oxides are stable. So by non-covalent interactions, by adding another one through non-covalent interaction, we can really able to make that. So unlike xenon oxide, this did not denote when subject to thermal and mechanical stresses. That's suggesting that the shock sensitive behavior of xenon oxide can be tamed when coordinated to appropriately. This is what recently the research is going on. Okay, these are also recent research. Okay, I think 2-3 years before I took this paper. Okay, you can see the Nobel case chemistry. Okay, VAP papers. These are all VAP papers. Okay, that it tells you it later comes to the textbook. Okay? This is what I want to show to you. Okay, you can really have to say family. Okay, so then the last one. That's what I said. The only the helium. Okay, the only the helium which can able to only the helium which can able to retain its nobility. This is up to 2017, up to 2017. But in 2017, there was a report in Nature Chemistry that helium also loses its nobility. Okay, okay. Helium also loses its nobility. Okay, the reaction is very beautiful reaction, very costly reaction. Okay, not only beautiful experiment. It's a very costly element. Okay, what they did, these are all diamond. Okay, you can read it. React with nobility, nobility. Helium, the most noble of the noble gases. Okay, up to 2017, there is no helium compound. There is no helium-based compound. So helium, the most noble of the noble gases, had only been co-oxidized into forming molecular ions or van der Waals compounds. It has now been seen in a stable solid compound, anyway to helium under high pressure. Anyway, whatever may be there, low pressure, high temperatures, they are able to make the compound, a solid compound, okay? A solid compound with helium, okay, helium. The experiment, okay, it's very beautiful experiment, okay? They are all the diamond, okay? These are all diamond, okay? These are rhenium, okay? One of the, okay, how to say, the strongest metal, the rhenium cascade. So here in the keyword, but they put it is sodium as well as helium, okay? Then they pressed it, okay? This is just pressed it, okay? When the diamond is the strongest one, to press it, okay? Then this is diamond is the transparent one. Then you can pass the X-ray here. If you get any product, you can analyze it here. That's what it did, okay? So how was it? How was it done? I just took it from the okay. In the experiment, they mixed small amounts of helium and sodium between a pair of diamonds and scaled the pressure million times the atmospheric pressure of Earth. The diamond is the strongest one. So the helium and sodium between a pair of diamonds and scaled the pressures million times the atmospheric pressure of Earth. Thereafter, the material was heated with a laser to temperature above 1200 degrees Celsius. It's really how to say it. I don't know how the helium can be able to. It's really cried, okay? Too much pressure, too much pressure, too much, how to say, temperature also. Okay. What is more, the resulting X-ray gave an idea of the compound structure that matched the computer prediction. The unusual compound is an electron. Okay. That means electron means if you have a compound where the electrons will be in the lattice size. Okay. The electrons are free, like anion. Anion is free, sodium cation is free. So the electron is one of the species. The electron is one of the species like anion or cation. That's what we say electron. And defining its bizarre nature. Okay, and you can see it here. Okay, I'll go to the next one. Okay, I'll read it after. Okay. Experiment and indeed observe the formation of the predicted compound from laser heated sodium loaded in the helium. Okay. Okay, what is here? Further analysis showed that this is okay. Some of the electrons in this one, okay, detach from all the atoms and localize incident at the industrial site, where they behave like anions. Okay, that means for example, if there is a sodium is the first group element. If there are two sodium means two electrons it will release. Each sodium will release each electron. So that two electrons acts as like anion material in which these occurs are named high pressure electrodes. Therefore, the NUT helium compound actually consists of three species. It's a solid species. You have a sodium cation, helium atoms, and these electrons. Okay, electrons. We predicted the structure like that. Okay, I don't know the nature of the chemical bond. I will read it. Okay, because the nature of the chemical bond of the NAP helium is very different from those in previously observed noble gas compounds. Noble gases have typically been seen to be lose their nobility by sharing their closed cell electrons with high electronegatividity elements such as fluorine and oxygen. This explains why the majority of the group 18 compounds are formed by heavier elements such as xenon and krypton, which are lower ionization layers. Okay, but what is here I will tell you. The another noble gases to lose their nobility as element, gaining electrons from alkali elements such as magnesium. Okay. The bonding in Na2H is very different from the other one. Here helium forms a stable compound with sodium. Okay, it actually does not chemically interact with it. Okay, absolutely. We are not able to remove electron from the helium or add the electron from helium. Okay, but the two electrons are removed from the sodium, and you have the sodium plus, and you have the helium, and you have the electron. It all forms the Na2 helium new compound. Okay, that's what they do. Helium forms a stable compound with sodium. It actually does not chemically interact with it. A charge analysis shows very small negative charge on the helium atom and Na2 helium, which can be considered zero within the accuracy of the method. So the bonding analysis suggests that the bond strength between helium and sodium and between helium and the electron is small enough to consider the null. Okay. But if you see it here, you can see helium here. Helium is untouched. Absolutely. Helium is untouched. But sodium loses two electrons. This loses one electron, this loses an electron. But anyway, then it forms the common. Anyway, what is the take home message is now we cannot say noble cases are noble cases. Noble gases, all noble gases except the 118 organelles, okay, which is highly radiated. How to say, maybe eight atoms, 10 atoms they have prepared. It will, with flick of eye, it will go. Okay, you cannot isolate. Okay, but now all the noble gases, okay, lost its nobility. Okay, lost its nobility. That's what I, during this main group chemistry teaching, I find these papers are very interesting. Okay, otherwise, whatever Professor Elias said, people will go mad by seeing a lot of equations. But this, I feel I can able to see to you people. Okay, my colleagues. So finally, I will come to the conclusions. I will come to the conclusions. I hope the time up. So let us cooperate. Chemically, we are non-covalent way. So what I want to say is, so the London dispersion force, other than this one, they are very weak, but non-covalent interactions play a major role for most of the compounds. Okay, that's what the few examples from the main group chemistry, in addition to this one, and conveying. So finally, I thank you all for listening to this one.
Thank you very much, sir. I think you have really tamped us by your presentation. I hope. I think everybody are very much attracted. That is what the chat box says that they have mentioned in the chat. Or some few questions are there in the chat box, sir. Can we proceed for the questions, sir?
Definitely, but I think there is no question. I'm only showing the paper, but yeah, of course, please.
Yeah. Again, a question from Megatachalam V. Is there any correlation between dispersion force, vapor pressure, and boiling point?
Dispersion force?
Vapor pressure and boiling point.
I don't know about that one. But so what I want to say is dispersion, this topic, what I want to say is the dispersion force, though among the weakest one, the London dispersion force, okay, but when you add more number, okay, that's what I said, strength is number, okay. I don't know about that vapor pressure and other thing which I didn't read it, okay. Let him read it. But my topic is the importance of London dispersion force, okay. Though it is a weak, it's the major one. That I really don't. I have to study. Let him study. No problem.
Comfortably, that I think. And one more is there. What is the minimal atomic bond distance for the existence of dispersion force? What is the minimal atomic bond distance for the existence of dispersion force?
That's a good question. That's a good question. No, why I am saying now absolutely there is no limit at all. Absolutely there is no. Why I'm saying when we say there is a London dispersion interactions, okay, you have the radii, okay, you have the radii, and this atom has a radii. Okay, you have the radii, you have the radii. When you bring this radii, if the distance is less than the RR plus, okay, then we say there is some interactions. Correct? Yes or no? You have one radii. This spherical has one radii. Okay, then another spherical has one radii. If you bring it together, then if you add it R plus R, if slightly less, then we can say there is some interaction. Otherwise, it won't interact. The radius will not decrease. Yes, the radius will not decrease. But what it says now, several cases, okay, several cases, the interaction is even, how to say, greater than the R plus of the diatomic molecule element. So now there is, that's what I'm saying now. Carbon single bond is 1.54. Now current it goes 1.8. It is more than the predicted one. But they say there is a sharing of sigma electron, covalent bond. So when it comes to the London dispersion force, most of the cases currently, okay, what they say, R plus R, okay, R plus R. Even that matter also you can say you have the London dispersion interaction. Okay, there is, okay. That's what I'm saying. Yeah.
I think only 2 questions are there, but everybody has. One more is there. Can we calculate hydrodynamic radii for ions? Can it be used to calculate diffusion coefficient of that ions?
Please let him read it.
Yeah. Sir, may I repeat? You will read or may I repeat? Can we calculate hydrodynamic?
Let him read it. Let him go home and read it.
Oh, you are.
Let him go home and read it. Okay.
Yeah.
If any questions
think,
related to the yeah.
If any participants want to interact with Professor Dr. Satyanthan, you are please, you can just unmute and then you can ask. Very tough questions they are asking.
No, that is not a tough question. That is not a tough question. But my lecture is only
they can read on themselves. That is what I am just criticizing the participants, sir. Please.
No, that's absolutely no problem. They have freedom to ask questions, but we have.
So that easy question that they can understand. Anyway, it is for teachers and
freedom to think ongoing interaction, but particularly speak of this slide.
Yes. So, any participant would like to speak to our resource person? Please let. Who is that? Satya Mahakrishnan, Dr. Satya Mahakrishnan. Would you like to talk to him? I think you have unmuted.
Yes, ma'am. Yes, ma'am. Actually, sir, this hydrodynamic radii, we are using this Einstein equation to calculate the diffusion coefficient. So, suppose if you know this scattering length or this dispersion length, from that can we calculate the hydrated radii? Suppose we are putting the ions in the hydrated form. So,
Ma'am, absolutely, I have no idea, ma'am. Okay. Absolutely no idea. So my questions, I bring this Heisenberg uncertainty principle to say that. So
okay.
to say that electrons are moving, it is not constant. If you want to explain the London dispersion force, you have to bring the Heisenberg uncertainty principle where position and momentum cannot be determined at the same place. So the electron clouds move continuously. So this I brought that one only to explain how the nonpolar molecule will create instant dipole because of the movement of electron. That's what I bring Heisenberg uncertainty principle. So this talk is absolutely not related to your questions. Okay, please.
Okay, sir. Thank you, sir. Yes.
Any other would like to interact? I think maybe because of the weekend Sunday, all we need to wind up, I hope. So, sir, thank you very much, sir. I think really you have tamped us with your informations. It is like even any people who are not in the field of inorganic can understand. I will not forget about this xenon oxide bond now. It has registered now very strongly. I hope everything like this, every point will be registered to the participant very strongly. So I take this opportunity to thank you, sir. I think is somebody. Yeah, nobody is there. Okay. So now I request our Dean, Professor Dr. M. Pradapachandra Kurup, sir, for the concluding session, sir. Over to you, sir.
Good afternoon, everybody. We have come to the close of third day's FDP program, and we have had two very good lectures by eminent speakers, Professor Anil Elias and Professor Satyendran. They have dealt with the main group and also the noble gas chemistry in a very simple manner. I thank both the speakers for the excellent talk and also very nice interaction. I'm also thankful to our HOD for coordinating this event, and I also thank Dr. Bhagyalakshmi for chairing both the sessions, and I thank all the participants for your valuable presence and nice interactions. I thank you all.
Thank you.
Thank you very much, sir. I think we can end the session, today's technical session, and I hope you all.
Yeah, I think we can conclude today's session, madam.
Yes, sir. Yes, sir. Please, sir. I thought you.
Hello.
Yes, sir. Yes, sir. Please, sir. Please, sir.
Yeah. So tomorrow we can again ask them to join at 3:20. So tomorrow also again 2 eminent speaker. So one is Professor Nadarajan from IISc Bangalore. Then next one is Professor Guru. What is his name, madam? Guru Sangar
Gunasegaran.
from Madras University.
Dr. Gunasegaran from
sorry, Professor
Madras
Gunasegaran from Madras University. Professor Gunasegaran from Madras University. So first lecture will be by Professor Nadarajan sir. He agreed. Okay. So all of you joined in time. Okay. Okay, madam. Thank you for
Thank you,
coordinating. Yeah. Yeah.
sir. Thank you,
Okay.
sir. Thank you very much, sir. I think shall we close the session, sir? Can I
Yeah,
ask?
we can close.
To close? Yes. Thank you. Thank you very
Yeah,
much.
yeah.
We'll meet tomorrow.
Yes, sir.
Yeah, you can close. Yeah.